Hello.
Sorry, कोई बाहर पैनल का बना हुआ है ना, you have to press
Yes,
escape. हाँ.
Okay. So, good morning, everyone. My name is Kaustav Rudra. I'm an assistant professor in the Department of Artificial Intelligence, IIT Kharagpur. Today, we are going to talk about this advanced prompt engineering. Okay. So, before going into this particular topic, let's have a quick background check. Uh, So I guess all of you so far use these LLMs in some ways. So let me understand that which one are basically popular ones. So you can basically give which one you have used among these LLMs like ChatGPT, Gemini, Cloud, Perplexity, or if you haven't used any so far. Okay. Okay. So it seems like this ChatGPT and Cloud, they are very popular for the users. So now let's see that how can we use these advanced prompt techniques with your popular LLMs. Okay. So what we are basically going to cover in this particular lecture, first we will cover the foundations, that what is basically prompting, what are the controlling parameters of that, basic prompting techniques like zero shot, few shot prompting. After that, we will go basically for the reasoning based techniques like chain of thought, self consistency, tree of thought methods. Then we will check basically actings and tool-based case like React. And finally, we will check the steering models like meta prompting and directional stimulus prompting, which are mostly aligned with the structures of the prompts. So, what is basically prompt? It is basically programming with a natural language. Okay. So why? Because we are giving the instruction, we are specifying the constraints, we are defining the inputs and output patterns, we are controlling the behavior of the LLM and iterating to improve the results unless and until we are satisfied. Okay. For example, if we write a traditional code that is basically sorting, what are the parameters that we have to pass? We have to pass the numbers, and what are the way we want to sort, we have to pass. Either we have to be descending order, it should be the ascending order, whatever. Now, if we want to do using the LLM and prompting techniques, it is basically simple in natural language text. You can tell that, okay, sort these numbers from largest to smallest and explain the steps. Now, what is basically prompting? We basically put an input into a format that encourages the model to carry out a task. For example, say X is the input, which is basically I love advanced NLP. What is the fx? Fx is the function that basically takes the input X. So classify this sentence's sentiment as either positive or negative, and you are passing the input that I love advanced NLP. And what is the output you are basically getting? That the sentence is positive. So ultimately, what does basically this LLM do? It is basically a function p theta y given fx, right? Y is the output that you are getting, x is the input you are passing, and fx is the prompt that is basically creating out of it. Now, what is autoregressive language model? So an autoregressive language model is an AI model that generates the text one token at a time, always predicting the next token based on everything that came before it. That means if we are thinking about a natural language text or something, we are basically processing word by word. So when we are basically spelling a word or basically predicting a word, it depends on the previous context. Okay. So a token can be a word, it can be a part of a word, it can be a punctuation or even the spaces or symbols. So the probability of a whole sentence is built by repeatedly predicting the next token from the previous tokens. For example, if I basically tell the cat sat on the fill in the blanks, okay? So some way I have to predict the next token out of it. So what are the possible next tokens that could be here, okay? So like if you ask the LLM to fill in the next token, so the next token is dependent on the previous context. And what is the previous context? This the cat sat on the, this is the previous context. On a similar note, when it predicts this particular word, that is basically this the, what is the previous context? The previous context is basically the cat sat on. Similarly, when it predicts on, it basically gets the previous context, the cat sat. So given this particular sentence, the cat sat on the, we have to basically predict the next token. And what are the possible options for the LLM? It might say that, okay, mat, the probability is basically 62%, floor is basically 15%, chair 8%, roof 3%. So this is basically, these are the tokens like mat, floor, chair, roof, and what are the probabilities out of it? These are the associated probabilities that LLM is predicting. And now, how does the generation look like? So initially it starts with the, then it predicts the next token, which is basically cat, and then using this the and cat, it predicts the next token, which is basically sat. Then it takes the cat sat, it predicts the next token, which is basically on. Then basically it takes the cat sat on, it predicts the, and finally it takes all these things and predicts the next token, which is basically mat. So this is basically an autoregressive language model that predicts the next token based on the previous context. Okay. Now, the question is, what is a prompt? So, prompt is basically initial text inputs given to a model, which it uses to generate the responses or accomplish the tasks. A prompt serves as an interaction point between a user and an LLM, allowing the model to generate the specific outputs based on the input provided. So, you can also think about our search engines when we basically search something or basically get the response from the internet. So we basically specify our query to our search engines and then we get the responses. You can also think about this prompt. It basically serves as an interaction point between user and the LLM, and based on this particular prompt, you are supposed to get the response from the LLM accordingly. Okay. Now, how does this prompt look like? It can take various forms, including questions, comments, text snippets, or even code, and can range from single words to complex paragraphs. Okay, let's have a look. So you can directly ask a question. What is a language model? That is also a prompt. You can also give a comment like write me a story about full moon. This is also a comment. You can also ask a particular classification questions like classify the following sentence on the basis of positive or negative sentiment, and then basically you are giving the input, that is the sentence, what a beautiful day. So it is a prompt with the text snippet. You can also ask for the code generation, like write a Python function that takes two numbers as input and return the sum of the two numbers. You can also ask for the code conversion, like you are providing a code in Python and you can ask that convert this particular code to C or C++. So these are a couple of examples, but all these possible cases are applicable when we are basically defining the prompt. Now for LLMs, we can generally define two types of prompt. One is basically system prompt that basically provide clear guidelines to the model on how to respond to the user inputs. And another part is basically user prompts, that is inputs by end users to interact with the AI system to obtain the desired outputs. So basically, what is the difference between this system prompt and user prompt? So system prompt basically set the context for the user to query the LLM, and then accordingly user can ask these questions to the LLM. So if you take a small example, that if a user decides that, okay, I am going to ask the medical related questions to the LLM, you can set the context that by a system prompt, that you can give this prompt to the LLM that you are a medical helping assistant and respond to the queries to this particular medical questions. And after setting that particular context using the system prompt, user can ask different kind of medical questions to the LLM. And what is your expectation? That as you set the context that you are setting the LLM for the medical related questionnaires, if user asks any other kinds of questions, that will not be responded by the LLM during that particular session. Now, The effectiveness of a prompt directly influences the relevance and accuracy of the model's response. That is quite common. It is also quite common for our browser. So the good you are in specifying your intent to the web browser, you will get the search pages accordingly. And similarly in the prompt, if you specify your requirements clearly in the prompt, you are basically helping the LLM to understand your intention, and accordingly LLM will respond with the correct format and the correct output. Okay. Now, well-structured prompts help the model understand the user's intent better. So it is particularly the user's intent. If you are able to clear your intent to the LLM, and you expect that you would get your result in the desired format. Fine. Here are the couple of cases of the prompt. You can also ask for the summarization, like summarize the following text. The quick brown fox jumps over the lazy dog. And you can particularly give a particular document, and you can say that, okay, I need a summary of 50 words or 30 words, whatever you want, and you can expect a response from the LLM accordingly. You can also ask for the personalized recommendation kind of thing, like recommend a book for the mystery lover, and you can expect a response from them. Similarly, you can ask for the evaluation, like this is a sentiment classification task. You evaluate the sentiment of the following review. This product exceeded my expectations. So what is the response? It is positive, negative, whatever. You can get that response from the LLM. Now, what is basically prompt engineering? Prompt is so far clear. It's a natural language text that you can specify to the LLM to accomplish your task. Now, it can span across various kinds of formats like code generation, summarization, personalized question, comment, many things could be there. Okay. Now, what is basically engineering? The engineering term in the prompt engineering is used as it involves systematic prompt design process optimized for the task at hand that is achieved through iterative refinement. So, what does that mean? That systematic prompt design. So maybe the first prompt that we use, we may not get the desired response. And based on the response, we can basically think that what are the modifications or what are the adjustments that we have to make to our prompt. And finally, how can you get that? One of the ways that iterative refinement can help you to adjust your prompts. And carefully crafted prompts help to users' intent better. Okay. So ultimately, through this refinement or through this iteration, what you are basically doing, you are helping the LLM to understand your intent better. So if LLM is able to understand your intent, it will basically, it will be able to give the response in a more precise way to you. Now, what are the common LLM inference terms that we can focus on? One is basically the token. Second is basically temperature. Third is basically the top K. And fourth, basically top P. So basically these two are related to the sampling, how we are going to sample the next token in the autoregressive model. Token is basically how we are going to process the input prompt or input text. Temperature is basically a controlling parameter that decides how LLM should respond to the user query. Okay. So let's have a look on them. Tokens. They are the basic units of the text that LLMs process. They can represent words, subwords, characters, depending on the tokenizer used. Okay. So it varies across the LLM. It is not a sacrosanct thing, but mostly it is might be word, might be subword, might be characters, whatever the tokenizer you are using. So for example, this is a particular text from the GPT tool. So pseudo hypoparathyroidism and deoxyribonucleic acid methylation affect mitochondrial dysfunction in immunocompromised patients undergoing chemotherapy treatment. So this is basically a medical document. If you ask the GPT tool to tokenize it, you can see the kind of tokenization you are getting out of it. So altogether, you are getting basically 33 tokens. And this is basically just a number, the number of tokens per 100 character. Okay. Now, in this particular tokenization, you can see one pattern. Okay. So some of the tokens that are basically standard English term that remain as it is. For example, this patients. Okay. So it becomes a particular word and it is also a token. Now, what about basically this methylation? So in the methylation, you can see there are two parts. One is basically this methyl. Another part is basically So this particular word, methylation, it is a single word. But how many tokens we are getting out of it? We are getting two tokens. One is basically methyl, another part is Asian. Similarly, other terms, say dysfunction. This is also a particular word. And how many tokens we are able to get out of it? So basically, I am getting a single token. So this word is basically represent a token. So what is the takeaway from that part? So the word and token, they are not same. Okay. So a particular word can be split into subwords that might work as a token. Similarly, this is another example you can check that the transformer-based model achieved 94.7% accuracy on 1000 test cases, outperforming GPT-2 by 3.2x. Okay. So here also you can see these patterns that whatever the standard English terms that remains the same in the tokenized form, like the transformer cases and this test. On the other hand, when you are getting this kind of thing outperforming, it is basically gets split into two parts. One is basically outperform, another part is ing. Okay, so these words are basically split into subword tokens. So here it is getting around 31 tokens. Now, what is subword tokenization? The goal represent the text efficiently while handling both common and rare words. Common words that are basically very frequent words in the English dictionary, rare words that is not frequent in the dictionary. What is the principle here? Frequent words remain whole. For example, this transformer. Okay, so it is basically remain as it is, the word. It is, and that is also the same as the token. Rare words are split into meaningful subwords. For example, this methylation. You are getting two tokens out of it. One is basically methyl, another part is Asian. So these are the basically subwords. Now, whether this methylation, it will be split into these two particular subwords, methyl and Asian, it depends on the LLM you are using. So this tool that we have used is basically GPT toolkit. Okay. Now, if you go for the other LLMs, that could be Claude or basically could be Llama, could be Mistral, the tokens might be different. So this tokenizer is basically LLM specific, and based on that, we'll get the output. Okay. But more or less, the format or the pattern remains same. Now, this is about the tokens. Okay. What is the second controlling parameter? Temperature. It is an important parameter based on which you are getting the response. So what is temperature? It controls the sharpness of the next token distribution, any positive values, lower temperature sharper distribution, and repetitive generation. Let's see what does that mean. So for example, suppose we have to predict the next token and we have, okay. So let's see how basically temperature controls the output. Okay. So suppose we are basically doing this same problem that the cat sat on the, and we have to fill the next token. And what are the possible options? Suppose we have basically 9 possible options that we have to fill one word out of this 9. And what is the probability out of it? So you can see that if your basically temperature is low, it is basically giving almost high weightage to the 9th word, whatever it could be. On the other hand, if you are basically increasing the temperature value, all the words become more or less equally probable. For example, this distribution is becoming more or less uniform compared to this kind of peak distribution or basically tail distribution. So if you are basically lower the temperature, it is basically sharper distribution. Sharper means one particular token will be favored. Okay. And what is the issue of that? If you try multiple times, you might get the same thing. So that is why it is called the repetitive generation. On the other hand, if we are going for the high temperature, our distribution become more or less uniform because all these tokens, they are getting some sort of probability now. Okay. And the chance of repetitive generation is less, and the distribution is also now become more or less uniform compared to the sharper distribution. Okay. And here you can notice the entropy is less because it is particularly concentrated on one particular token. Here it is uniformly distributed, so this particular distribution, it has more entropy. Now, let's have a look, okay? How we can decide the probability of the next token. So temperature scaling in the softmax, okay? So whatever these probabilities that we have seen earlier, 62%, 18%, something, how can we get these probabilities? We can apply the softmax on the log it scores. So what you are getting for the particular token I, you are basically doing exponential of Zi divided by T. T is the temperature. And what you are doing, you are normalizing across all the tokens. So for example, if you look into the previous slide, there are basically 9 possible options. So for each of these tokens, you have one probability. Okay. So let's take a small example. Suppose we have these 4 tokens, like this cat, dog, fish, banana, etc. Okay. And what is the logit score that we are getting out of these 4 tokens? The cat, the score is basically 4.0, the dog is 2.0, fish is 1.0, and banana is 0.0. These are the logit scores, these are not the probabilities. So we have to basically convert them to the probability using the softmax technique. Now, what is the basic softmax technique? The T will be 1. If we do that, what is the probability out of this? So T means you can get this equation exponential of this Zi by the summation of the exponential of the Zj. Okay. So here the cat gets the probability of 0.831, dog 0.112, fish 0.041, and banana is 0.015. And what is the entropy out of this? That you are basically familiar with this equation, that is P log P. Okay. So basically P and then basically log. So if you do that particular equation, you can check the entropy of this particular system is basically 0.594. Now the question comes that if we increase this particular temperature and if we decrease this temperature, what is the entropy or what is going to happen? So let's first see that if we basically reduce the temperature. So that means suppose I am reducing it to 0.5 instead of 1. In that case, what is the probability? You are giving more weightage to the cat. Obviously, this probability is basically getting less weight. And what is the entropy? So you can see the entropy basically goes down compared to this 0.59. Similarly, now on the other way around, if I increase the temperature, you can see now the distribution becomes more flattened. So here you get 0.579, 0.213, 0.129, 0.078. And if you get the entropy, what is the entropy now? It becomes 1.109. So it is basically increasing. So this is the idea that this is the basic softmax operation standard. Now if you reduce the temperature, you are getting more sharper distributions, and basically you are pinpointing to a particular input. So basically you have less doubt, so your entropy is less. If you are increasing the temperature, then what is going on? If you increase the temperature, then you are flattening the distribution. More than one token become probable, and entropy is going to increase. Okay. So this is basically decreasing direction. This is basically increasing direction. Now, with this idea, you can see here what is basically going on if we basically increase the temperature. Okay. So in real life, we basically hardly go for temperature from 0 to 2 range, but this is just for pictorial representation. If you basically vary the temperature, so you can see the distribution basically from a sharper distribution, it becomes more flattened distribution. So what is the intuition for that? It scales the logits of the tokens. Okay. From the logit score, it basically scales it to some particular probability range. Temperature is equal to 1 is the basic softmax that uses the same as the predicted logits. Temperature is much greater than 1. It predicted the logits have less effect on the softmax output. Okay. If you increase the temperature too much, then you are particularly pointing to a particular token, because you are almost reducing the entropy and your entropy almost goes down to 0. Another problem is there. If I am basically reducing it, what will happen if T become 0? So this temperature is equal to 1 is the basic softmax operation. If you increase the temperature, your distribution becomes flattened and you are basically increasing the entropy. On the other hand, if I am reducing the temperature, how far we can go? Okay. So if someone says that, okay, I want to set T is equal to 0, obviously you can see due to the divide by 0 problem, we cannot make it T is equal to 0. So in that case, what can be done? You can add a small threshold value like say 0.00001 so that you should not have the divide by 0 problem. And if you basically reduce this temperature to that extent, then you are basically doing a greedy coding. Greedy coding means you are particularly pointing to a particular token and others will not come. So in this particular chart, you can see when the temperature is low, only the 9th token is there. And after that, if you increase the temperature, the other probabilities start to come. Okay. So this is the idea. So what is the takeaway from there? T is equal to 1, you have the basic distribution. If you reduce the temperature, you are basically sharpening the distribution, you are pointing to a particular token, your entropy will be less. Model is less confused. Model knows that, okay, I have to pick this particular token. If you increase the temperature, you are basically flattening the distribution, your entropy is increasing. Model is also confused like which one to choose, but you give more option for the model that it can select any token out of it. Okay. So this is the way temperature basically controls the next token generation of the LLM, and it is basically an important controlling parameter for the LLM. Now, fine, based on the temperature, I am selecting certain tokens, but ultimately I have to fill the next blank using only one token. So how can I choose that particular token? Okay. So one of the idea is the top k sampling. Okay. So top k sampling involves selecting the top k most likely words from the probability distribution and then sampling the next word only from this subset. Okay. Now the question is, the sun rises in the fill in the blanks, that I have to basically fill this particular blank. Now how basically LLM is going to fill that particular blank? What is the possibility? Okay. So one of the idea is basically it has to find out a word. Now the question is, from where it can find a word? So LLM, it has its vocabulary. So all these LLMs, they are trained on certain vocabulary. So it has some vocabulary, which might be 40,000 words, which could be 50,000 or something, that varies. And ultimate, if I leave it a very basic task, it has to pick one particular word from that particular vocabulary. So what is the probability in that case? So it might be 1 by 40k. Okay. So if you basically want to choose from the entire vocabulary. Now what basically, but you can understand that based on the context, all the words are not possible or basically feasible. Okay. So how can I basically make this particular set very crisp, that from this 40k, I would like to reduce it to a particular number. And what is that number? That number is basically a simple k. How can I do that? So suppose in this particular example, the sun rises in the fill in the blanks. This is the probability distribution. Okay. Like east is basically getting the highest probability with 0.19, morning is basically 0.17, sky is 0.15, distance is 0.14, glow is 0.1, and then subsequently you have the other words like vastness, space, down, planet. In this way, you have all the vocabularies, whatever is your size. They all have certain probabilities. Might be very close to 0, but they have some probability. Now the question is, when I have to sample the next word, how I am going to sample? So if I set that, okay, with top k sampling, where k is equal to 5, the model would only consider the top 5 words with the highest probability for its next output. So in this particular case, out of this entire vocabulary set, which is about 40k, the model is going to sample the 5 words. So what are those 5 words here? These are the candidate tokens: east, morning, sky, distance, and glow. These are the tokens. Now what model will do? Model will take this candidate set and it will sample one particular token out of it and fill this particular blanks. So this is basically the idea of the top k sampling, and this method reduces the chances of generating highly improbable words and provides a more controlled and predictable output. Now, what are the highly improbable words? All these clip tail parts, they are basically improbable words. So basically you can skip that. You can focus on this candidate set, that is k is equal to 5, and you can sample one out of it to fill the blanks. Now k, it is in your control. You want to say k is equal to 3. What will happen? in that case, this is basically your candidate set, that is east, morning, and sky. If you tell that, okay, I want to be very precise and I would like to go with only one token, what is basically your set? I'm going to go with top one. Top one means there is no chance for the LLM to do any kind of diversity. You are basically fixing the token that has the highest probability. That is basically the east. So from this part, you can see if you reduce the value of the k, your diversity will be less because you are reducing the numbers that LLM can choose from. If you increase the k, the problem is if you increase the k too much, you are bringing redundant tokens that are not necessary. So you have to maintain a balance that whether you would like to go with a very small k or basically k large. Obviously, k large is not a good option. And if you want some kind of diversity, very small k is not also a good option. You have to fix a balance between them, 3 to 5 or something like this. So this is one of the sampling technique, top k sampling. Okay. Now, what is the other way of doing this sampling? We call it top p sampling, or sometimes we also call it nucleus sampling. Okay. In top k, we have to specify this number, and sometimes we are not sure what should be that number is, right? How to say that k is equal to 3 would be good, k is equal to 5, or k is equal to 7, because it depends on the text and the problem or also the LLM. There is no sacrosanct answer for that. So for that, we would like to take the help from the probability distribution. So this nucleus sampling tells that instead of selecting a fixed number of top words, the model selects a subset of words that have a cumulative probability exceeding a certain threshold p. For example, I am taking the same example, the sun rises in the, and I have to fill in this particular blank. How can I do that? This is basically my probability distribution of the next token. East, it is getting the highest probability 0.19, morning 0.17, sky 0.15, distance 0.14, like the same way in the last part. But now the question is, I can now specify a cumulative probability distribution. For example, here if I mention that I want to take a probability up to 0.65, I do not want to go beyond 65. I am not specifying any particular number of tokens. I am just specifying that I would like to take a probability mass of 0.65. I would not like to go beyond that. So then what we will do here, we will start from the beginning, 0.19. Then what is the next part? 70. So basically, if you sum them up, it will become 0.36. If you take this, what will happen? 0.51. And if you add this, it will become 0.65. So if I specify that, okay, my probability mass limit is 0.65, you are restricting yourself to this 4 tokens. Okay. And these top 4 words in the probability distribution cumulatively account for the 65% of the probability mass, and we set p is equal to 0.65. The model would sample the next word from this set of 4 words. Now, these 4 words are basically candidate tokens. So, means they are basically the competing ones. Now, which one will basically go here? It basically a random guess from the LLM. So, out of these 4, the LLM will choose one of them to fill this particular blank. So in the top k, I have to specify a number, 5, 7, 3, whatever. In p, I am basically specifying a probability mass. I am not specifying any number. Okay. So here, if you say p is equal to 0.65, this is basically your 0.65, and model will choose one of them. And so last time, this is basically your clip tail, and you are doing the sampling out of them. Now, if you say like, okay, I would like to be very much decisive or basically fix. So in that case, I can reduce this number. Okay. If I just keep 0.36, what will happen in that case? You can basically easily guess 0.9 and 0.17. That means 0.36. So in that case, your candidate set will be east and morning. Rest of the part will be your clip part. Now, what will happen if I mention 0.40? So then you can see 0.19 plus 0.17, 0.36. Still, I have mass left. How much mass I have left? 0.04. If I take 0.15, what I am getting? 0.51. Obviously, I cannot take this one. In that case also, your basically candidate set will be this first. That out of this probability mass of 0.40, I can only take this first 2 tokens out of it. Now, like last time, you can also see if you set the probability mass very low, you are basically going for a decisive one, because in that case your candidate set might contain only 1 token. and LLM doesn't have any option. It has to just select this one. So how much probability mass you would like to give, based on that your diversity will also come. How this diversity will come? If your candidate set is at least basically 4, 5, LLM has an option to choose one out of it. So it may bring the diversity to your next token. If you keep P very small, you have only one token, there is no diversity, LLM has to go with that particular token. So this diversity and specificity that you have to control by varying your P value. Okay. So this top P is more dynamic than the top K, adapting the subset size based on the probability distribution. Because in top K, you have to specify a number and you do not know this probability distribution. What is the problem in the probability distribution? You do not know the scores 0.19, 0.17, 0.15, 0.14. If it is a very complex sentence, it may happen you are getting this kind of thing. Maybe the topmost one, it is getting point probability of say 0.06. The next one might getting 0.06, again 0.06, then could be 0.05. In this way, it could be like this. So if you are basically specifying some top P, you can decide that which one or how many tokens I can go for. Top K might be little bit challenging for those particular complex cases. Okay. Okay, fine. These are the two sampling techniques that we can go for the next token selection. Now, it can capture more diversity in outputs, reducing the repetitiveness. Okay. Now, let's see some kinds of prompting quickly. So, what are the types of promptings? So, basic prompting you are already familiar with and you have used this zero-shot prompting. It is basically simple and direct. You can go to the LLM and basically ask some questions on your own. What is few-shot prompting? Before asking a question, you are basically giving some kind of example to the LLM so that LLM can understand that, okay, what kind of question the user is asking. Now we can go with the more advanced kind of prompting like chain of thought, where along with the input, output, we are also focusing on the reasoning process, the thought process of the model. Finally, we are going with the advanced patterns or basically prompts that could be React or tree of thought, structure oriented prompting. All these things basically come into this particular paradigm. Okay. So it will go into this particular direction. Let's start with the very basic one, zero-shot prompting that you are already familiar with. So what is basically zero-shot prompting? Say the user is there. It says that, okay, classify the test into neutral, negative or positive. Just give me the classification. And then you are giving your input text that I think the vacation is okay and you are expecting this sentiment. And suppose this particular LLM, it is basically giving you the output. This is a neutral sentiment. Now the question is why it is basically zero-shot? Because I didn't tell the LLM that, okay, how to solve the sentiment detection problem, how you should identify the sentiment, and I am just telling that this is my input and what are the possible options you have. It could be neutral, it could be negative, it could be positive, and you have to choose one out of it. The LLM is smart enough and it says that, okay, it seems to be neutral. So direct instructions, user tell the AI what to do without providing any specific examples or how to solve the task. User is not telling the LLM. It relies on the pre-trained knowledge. LLMs learn to perform tasks from massive datasets, enabling them to generalize to new unseen instructions. Okay. Versatile and adaptable. Zero-shot prompting makes AI models useful for a wide range of applications without task-specific fine-tuning. Okay. So you can see we are not fine-tuning anything, we are not giving any example, we are not telling LLM how to solve a problem, we are just directly asking the question to the LLM. Okay. Now, how the size of the LLM affect the performance of the zero-shot prompting? Okay. Generally, model size matters. Larger LLMs are better at zero-shot tasks rather than smaller LLMs, okay? Because larger LLMs, they are trained on more amount of data and then they have more parametric memory. So they are already familiar with more amount of tasks than the smaller one. Now let's see whether zero-shot prompting is enough or not, okay? So now let's ask a question to the LLM, okay? They solve this math problem that what is the 3 by 7 of 84? This is the question that I am asking. All of you know the answer, that 3 by 7 of 84. Now let's see how does LLM solve this problem. Now LLM is telling that to find the 3 by 7 of 84, we can use the multiplication property of the fraction. So first let's multiply the numerators. So it is multiplying 3 with 84, it is getting 252. Okay, fine. then it is telling next it's multiply the denominators. So it is basically 7 multiplied by 84, it is getting 588. Now it's telling now multiply the products, but although it is telling that I am multiplying, but ultimately it is basically dividing the product. Okay. And then to divide two numbers, we can use a calculator or long division, and it is basically dividing, and it is basically giving the response that 3 by 7 of 84 is approximately 0.4286, which is basically not correct. So you can see where the mistake starts to happen. So this particular thing is not important. Okay. From this point of action, the entire flow becomes wrong, and ultimately it leads to a wrong answer. So then what is basically the observation here? Zero-shot prompting can struggle with complex tasks where implicit knowledge of the specific examples are needed. Okay. So during the pre-training process, LLMs may not be familiar with this kind of mathematical reasoning problems, so that it is not able to generalize the task well for the user. Lack of context can lead to vague or imprecise responses, difficulty in understanding the nuanced instructions. And what is the solution in that particular case? Providing examples, it could be few-shot prompting, can significantly boost the performance on the challenging task. Now, what is few-shot prompting? As you know, this name, that okay, before asking some question, at least give some kind of input to the LLM, so that LLM can understand that what kind of task I am going to solve, how does the input look like, and how does the output should look like. Okay. So let's see that how few-shot prompting can help there. Okay. So here I am basically giving this particular input. This is awesome, / positive. Okay. So this is basically my input. This is basically a marker. This is basically my output. So this is basically input-output pattern. What is input-output pattern? Input, output. Okay. Next one I am giving, this is bad, negative. Wow, that movie was rad, positive. Now I am asking what a horrible show, and you have to basically fill in that particular blanks. Now the model is telling this is basically a negative sentiment. Now what is this first three? These first three are basically my few shot examples. Okay. So this helps the model to understand that what should be the input and what should be the output, and in the output what I have to predict. So what does model learn from these first three? That the possible options are basically either positive or basically negative. And this first part before this double marker is basically my input, and after that the output will begin. So when I am giving the fourth input, it basically predicts the next token. Now for LLM, what is this part? It is nothing but the next token prediction. So it is basically predicting the next token, and it is basically predicting the next token as the negative. Now the question is, few-shot learning involves providing the model with a small number of high-quality examples that include both input and desired output for the target task. What are the benefits out of it? These examples help the model grasp the user intent and desired output format and style. Okay. What is the desired output format? This particular slash, then the output, this particular format model is learning from your input. What is the takeaway? Few-shot learning generally leads to more accurate and relevant responses compared to the zero-shot prompting. This is quite obvious because you are now making the LLM familiar with that kind of task that it is going to solve. Now, whether this particular part is fixed, the answer is no. If you want to change the pattern, that is also fine. So for example, after specifying the input, you can also mark some kind of other tokens like this questionnaires and then out. Then basically LLM would become familiar with that particular. Okay. Now let's see whether this few-shot prompting is enough to solve these complex problems or not. So suppose I have this particular mathematical problem. It says that the odd numbers in this group add up to an even number. This is the sentence. Now what are the numbers in this group? 4, 8, 9, 15, 12, 2, 1. And you are telling the odd numbers in this group add up to an even number. Let's see whether this statement is correct or wrong. So what are the odd numbers? 9, 15, 1. So if I add them up, what will be the output? 25. Now 25 is not an even number, so I am giving the output, the answer is false. Now, how I am solving this problem, that I am not mentioning to the LLM. I am just telling the final answer that it is not false. It is not correct, it is false. What is the second input? The odd numbers in this group add up to an even number. What are the numbers? 17, 10, 19, 4, 8, 12, 24. Now, if you basically add them up, what is the output? 17, 19, 36. So, it is basically even number. So, the answer is true. In this way, you are giving two more inputs to the LLM. And then finally, you are asking the question that now the number sequence is 15, 32, 5, 13, 82, 7, 1. What would be the correct output? 15, 5, 20, 13, 33, and 1, 34, 7, 41. So if I take 41, it is basically an odd number, not an even number. So what should I expect from the LLM? The answer is false. Let's see what does LLM say. LLM says that, okay, the answer is true. So it is not correct, it is wrong. So that means these first four examples, we basically provide those examples so that LLM can understand the pattern. Pattern means how I am basically solving this problem. But from this final answer, you can see the LLM fails to understand that particular mapping, that how I am basically mapping this particular sequence to this particular statement, whether it is false or true. Now, when dealing with more complex reasoning tasks, example mathematical reasoning, this method may fail to deliver the correct output. Okay. In this example, we can check that it is not the correct response. It seems like few shot prompting is not enough to get the reliable responses for this type of reasoning problem. And what is the takeaway from that? Few shot prompting can help in solving certain kind of task, but it is not necessary that it will be able to solve complex reasoning problems or complex planning kind of problems. So this needs the complex planning. So planning means what are the parts or what are the steps if a user or basically if a human has to point out. Given this number sequence, the first sequence could be find out odd numbers. So this is the first step. What is the second step? Add these numbers. What is the third step? Check odd or even, and then accordingly give it true or false. Now the question is, these three steps, as a human I can understand these are the ways I have to solve. So it is not necessarily for the LLM to basically understand or decode that pattern always. It may understand this pattern for certain kind of problems, but it is not sacrosanct. Okay? Particularly for this problem, it is not able to do that. Okay? Let's see how can I overcome this problem. So with that idea, we come to the reasoning kind of model. So you may be familiar with this particular term. It is a quite popular prompting technique. It is called the chain of thought. So it is the reasoning prompt that we have. So without COT, complex math problems, you are getting direct answer. It could be sometimes right, sometimes wrong. So we do not have any control on that. With this chain of thought, we are going with this complex math problem. We are thinking step by step. We are basically break this problem down into the steps, like the steps that I have shown for the last problem, the three steps. Find out the odd numbers, add these numbers, and then check whether it is an even or odd number. Now, who will basically tell these steps? So we have to also make the LLM understand that when you are solving this kind of complex mathematical problem, you have to basically decompose it into the simple steps, like this step 1, step 2, step 3, and give the final answer based on those particular steps. So what is the technique here? It guides the LLM to solve the complex task by breaking them down into smaller logical steps. And how it works? The prompt encourages the model to think out loud and show its reasoning process, leading to a more accurate solutions. Because if it basically decomposes into the steps, it is also easy for us to understand which step the LLM is making the problem. And accordingly, we can focus on that particular step. Okay? What is the effectiveness? Especially powerful when combined with few shot prompting, providing both examples and a structured approach. Now let's see the same example. Now if we are going to go with the chain of thought reasoning, what is the difference and what is the output? Again, I'm asking the same question, that the odd numbers in this group add up to an even number like 4, 8, 9, 15, 12 to 1. But now instead of few shot prompting, we are adding the reasoning process. What is the reasoning process? You can see that I am also giving, adding all the odd numbers, 9, 15, 1 gives 25. So the answer is false. So I am not just telling the answer is false. Along with that, I am also adding the reasoning part. That is basically the steps. And in this way, I am giving the other input examples and also mentioning the steps so that LLM can figure out how to solve this problem. Now I'm asking the same question that I asked last time, that the odd numbers in this group add up to an even number. And what are the numbers? 15, 32, 5, 13, 82, 7, 1. Now let's see, last time we get wrong answer in the few shot prompting, whether this time LLM is able to give me the correct answer or not. This time I am getting this response. The odd numbers in this group are 15, 5, 13, 7, 1. Adding this together gives this 41. Since 41 is an odd number, the answer is false. Okay. Now you can see that now you can ask any questions or any sequence, you will get the correct answer. Why? Because now LLM is understanding the steps. So if it solves step by step, it will automatically give you the correct answer. But LLM automatically is not able to identify these steps. Once I specify this is the way to solve this problem, LLM can basically formalize into the steps. So like for these complex mathematical problems, we may have to add the reasoning process to help the LLM understand that what are the steps. For certain problems, definitely LLMs can figure out the steps by its own and it can help the problem. But for complex tasks, we as a human should guide the LLM how to solve it. Okay. If you guide for some problems, it will automatically generalize it for the other. Fine. So model size and complexity. Larger LLMs are generally better at chain of thought reasoning. COT prompting can elicit correct answers to complex questions as shown above when few shot prompting fails. Okay. And what is the key takeaway from here? Sophisticated prompt engineering techniques like chain of thought can significantly enhance the reasoning capabilities of the existing LLMs. Okay. Chain of thought is basically a reasoning technique. So where we are adding the input, we are adding the reasoning process, and we are also adding the output process. So this reasoning process helps the LLM to understand the solution activity or the solution procedure. Now, what are the variants of the chain of thought? Okay. So zero shot chain of thought. Now, before going into the zero shot chain of thought, let us understand what is the problem with this chain of thought process. Because we are basically addicted to the LLM. Why? Because we think that we do not have to tell the LLM how to solve the problem. We can ask the question and LLM can directly solve our problem. At best, what I can give the input and output, and basically I can get the response. But if I have to also tell how to solve the problem, that is basically a headache for me. Headache for me in the sense, we need more humans to annotate this reasoning process, annotate this data, and provide this reasoning process. Why? Because gathering these reasoning steps, it is not enough. Okay. So it is difficult. A human has to do that, and then you have to set it for the LLM. How many examples do I need? So it will basically add some extra overhead for the human. Can I automate this reasoning part some way? With this idea, this particular journey comes that, okay, what are the variants of the chain of thought? So one of the ideas is basically zero shot chain of thought. So zero shot chain of thought, what is the question? A juggler can juggle 16 balls. Half of the balls are golf balls and half of the golf balls are blue. How many golf balls are there? And the answer is basically 8. So this is basically simple zero shot prompting. I'm directly asking the question. As a human, you can get your answer. So we have 16 balls, half of the balls are golf balls. That means 8 balls are golf balls. And out of that, half of the golf balls are blue. That means only 4 balls are basically blue. But what is the answer I am getting in the zero shot prompting? I am getting 8. So some way LLM is not able to figure out the steps. Otherwise, the answer would be correct. Now, in the zero shot chain of thought, what I am doing? I am asking the same question, but this time I am also adding one small thing in the prompt. I am telling the model, let's think step by step. I am not telling how to solve the problem. I am also not giving you examples. I am just adding one simple text to the prompt. I'm just telling, let's think step by step. Now, if I just add this particular thing to the prompt, you can check the difference is the output. So it is basically giving you the steps. First, it says that, okay, there are 16 balls in total. Fine. Half of the balls are golf balls. That means that there are 8 golf balls. That is also fine. Half of the golf balls are blue. That means there are 4 blue golf balls. Now, once you basically get these steps, you basically become sure, yes, my reasoning process is correct. And once this reasoning process is correct, you can ask any kind of these questions, you will get the correct output. So what is the interesting part here? I do not have to give the reasoning part because that is cumbersome for a human to annotate those things. I just add this particular line. Let's think step by step. And if I just add this particular part into the prompt, automatically LLM figure out the steps through which it can basically solve the problem. And you can see this one is basically the wrong, but this one is basically the correct one. Now, simplifying the chain of thought, okay? No need to provide explicit reasoning steps in the prompt. I do not provide any explicit reasoning. I just add one particular sentence. Let's think step by step. How it works? Add let's think step by step to the original prompt. The LLM generates its own reasoning chain and uses it to arrive in the answer. So this is basically the automated reasoning step. What is the benefit or what are the benefits? Task agnostic. Applicable to a wide range of tasks without needing task specific prompts. You can see this is not a task specific prompt. You can ask any kind of other problems. You can just add this thing, let's think step by step. You can also ask a loss and profit question. You can simply say, let's think step by step. You do not have to give the solution for that problem. So that's why it is basically task agnostic. Okay. It encourages deeper reasoning. It promotes more thoughtful and structured problem solving by the LLM. Why more thoughtful? Because these are the thoughts it shares with you, and you can also understand that whether the reasoning process is correct or not. Okay. And what is the main advantage? Let's see. You automatically get this reasoning process from the LLM. You do not have to annotate it using the humans. Now, what are the other variants of the chain of thought? Few shot chain of thought. So what is the original few shot strategy? Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each cans have 3 tennis balls. So how many tennis balls does he have now? So you can solve this 5 plus 2 into 3, 11. So basically the answer is 11. So I am telling the final answer, but I am not telling how to solve the problem or what are the steps in solving that particular problem. And then I am asking the second question. The cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? You can get the answer 23 minus 23 plus 6, 9. Okay. Let's see. What is the variation in the few shot chain of thought? So here the same question is there, but in the answer, I am telling the reasoning process. I'm not just giving the answer, I'm also telling the process or the steps through which I solve this problem. That Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls. 5 plus 6 is equal to 11. So the answer is 11. Now I am asking the question. Now what is the thing? In this few shot prompting, I am getting the answer 27. And what is the part that I am getting in the few shot chain of thought? It is telling the cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20 is equal to 3. So they bought 6 more apples. So they have 3 plus 6 is equal to 9. So the answer is 9. Obviously, the answer is correct. So that means this reasoning process that I provided, it helps the LLM to find out the way I have to solve this particular problem. Here I am just telling the answer. LLM figure out certain steps, but the steps are not correct. And here it also doesn't reveal the steps to you so that you can understand where is the mistake. So that is the advantage in the few shot chain of thought. And what is another advantage out of it? Once you are getting this kind of responses, and if these responses are correct, you can directly use it for the few shot learning. You do not have to ask a human to annotate these reasoning parts for the LLM. You can directly get it from the LLM, and in turn you can use it as the input for the LLM. So with that idea, another variant of the chain of thought is the automatic chain of thought. So automatic chain of thought means Obviously, we do not want to involve humans to annotate this reasoning part of the steps. We can automatically want to get it from the chain of thought. Okay, so automate the creation of the reasoning chains, reducing the reliance on the manually crafted examples. It is a two-stage process. Okay, question clustering. Questions from a dataset are grouped into clusters based on similarity. This helps in identifying the representative questions for each cluster, ensuring the diversity in the examples. What does that mean? Suppose we have these questions in my set. While shopping for the music online, Joe bought three. Some statement is there. A chef needs to cook 9 potatoes. He has already. So all these questions are problems that are basically there. Now the question is, when I have to provide the examples to the LLM, obviously I cannot give everything. So I have to basically ensure that I select a diverse set of examples. How can I do that? So one of the idea is basically do the clustering of these questions so that similar questions get clustered into one part. So here you can think that this 1, 2, 3, 4, 5, these questions are basically similar topic or similar kind of thing. So they get clusters into one. In this way, if you do clustering, suppose you are getting k clusters. And then what you are basically doing, next step is demonstration sampling. So a representative question is chosen from each cluster. And how does that look like? So maybe from the cluster 1, you are selecting this question while shopping for the music online. From the kth cluster, you are basically getting this question. A chef needs to cook 9 potatoes. Now the thing is basically, do I have to involve human to get this basically reasoning process of the steps? The answer is no. You can simply tell, let's think step by step or let's think step by step. LLM can generate the reasoning process on its own that you can use for the in context learning process. Okay. Now, why this step is important? This basically ensures that you are getting diverse set of questionnaires or the diverse set of samples. Otherwise, it may happen that you are selecting all the questions from this particular cluster. Other clusters basically they remain neglected. So just to ensure that we are maintaining diversity from all the different fields, you first ensure a clustering process on the questions, select a representative question from each cluster, and then you can automatically generate the reasoning process from these clusters. This is called the demonstration sampling. And then you are using the zero-shot chain of thought to generate the reasoning chain. How you are using this zero-shot chain of thought? You will simply add this line, let's think step by step, and it will generate the reasoning process. For example, take this question. While shopping for the music online, Joe bought 3 country albums and 5 pop albums. Each album came with a lyric set and had 3 songs. How many songs did Joe buy total? This is the question. Okay. And what I am basically doing, I am just adding, let's think step by step. And what is the output I am getting from the LLM? It is telling Joe bought 3 country albums. Each album has 3 songs. So she bought 3 multiplied by 3 is equal to 9 songs from the country album. Joe bought 5 pop albums. Each album has 3 songs. So 5 multiplied by 3 is equal to 15 songs from the pop albums. Now Joe bought 9 plus 15 is equal to 24 songs in total. So the answer is 24. So that means first through the demonstration sampling, you are selecting this question. You are adding the prompt, let's think step by step. And you are basically generating this reasoning process from the LLM. This is called the zero-shot chain of thought. In this way, you can also generate the other questions. Like this might be from the cluster 1, this might be from the cluster 2. In this way, you are basically generating the responses. What is the advantage? This reasoning process is generated by the LLM. We do not have to involve a human to basically write these steps. That is the advantage. And then what I am doing, when I am coming for a particular question, I am asking a question that a pet store had 64 puppies. In one day, they sold 28 of them and put the rest into cages with 4 in each cage. How many cages did they use? Okay. So you have to solve this problem. So let's see if I add this prompt, let's think step by step. What is the output? So this is the test question. You are passing it to the LLM and you are getting the response that the pet store had 64 puppies. They sold 28 of them. That means that they have 36 puppies left, and out of 4 means 36 by 4, you need 9 cages. So the answer is 9. So what is the advantage out of this? This zero-shot chain of thought generates a reasoning chain for the chosen question. Okay. So you are selecting this from these different clusters, and you are adding this, let's think step by step, and you are getting this reasoning process directly from the LLM. And interestingly, this reasoning process help to get you the correct answer for this complex kind of problems. So this is called the automatic chain of thought. Why automatic chain of thought? Because I am automatically generated this reasoning process. So this is basically chain of thought. Now, what is the outcome? This auto COT achieves comparable or superior performance to traditional chain of thought and few shot prompting, especially for the reasoning task. Why? Because in the chain of thought, you have to ask a human to generate the reasonings or basically the steps, and obviously there is a limitation of that. You cannot basically annotate large amount of reasoning steps. In automated chain of thought, you do not have that binding. If you just add this particular line, let's think step by step, you can generate large amount of responses from the LLM, and it will help the LLM to understand the reasoning process of the steps automatically. We do not have to help involve the humans, or basically we do not have a burden on the data, and it will solve this problem of the reasoning process in an automated way. Okay. So that's why this idea is automated chain of thought. So zero shot chain of thought help you to get the training data, and automated COT, you can use it to boost the reasoning process. Okay. Okay, so let me end with this particular concept of the chain of thought, which is basically self-consistency part for the first round. So you are already familiar with the chain of thought prompting. So what is the prompt here? So you are basically giving the prompt, you are passing the prompt to the language model, and then you are basically getting the answer. Okay. So for example, if there are 3 cars in the parking lot and 2 more cars arrive, how many cars in the parking lot? So basically there are 3 cars and we are getting 2, 3 plus 2 is equal to 5. Okay. So here also it is a question. So you have certain things. So let's see how we are basically getting. So it says that Janet's ducks lay 16 eggs per day. She eats 3 for breakfast every morning and bakes muffins for her friends every day with 4. She sells the remainder for $2 per egg. How much does she make every day? This is the question. Okay. Now, why do I need this self-consistency, or what is the issue with this current kind of prompting? So what is the current kind of prompting? I have a prompt. I pass it to the large language model. Large language model basically generate a reasoning process and give me the answer. So this is basically only a single direction it can solve the problem. Now, whether I can solve the problem in multiple way and take the majority voting out of it, does that solve my problem or not? So let's see. So if I pass it to the language model, so the first idea says that C has 16 minus 3 minus 4 is equal to 9x left. So the C makes $2 multiplied by 9 is equal to $18 per day. So this is the first way LLM solves this problem. What is the second way it solves the problem? It tells that, okay, this means she sells the remainder for $2 multiplied by 16 minus 4 minus 3 is equal to $26 per day. What is the third path tells? So she eats 3 for breakfast. So she has 16 minus 3 is equal to 13 left. Then she bakes muffins. So she has 13 minus 4 is equal to 9x left. So she has 9x multiplied by $2 is equal to $80. So this is basically branch 1. This is basically branch 2. This is basically branch 3. Now I am basically showing one example and I am asking the question. I am passing it to the LLM. Now instead of this basically single direction, it is basically solving the problem using multiple ways. This is the first way, this is the second way, this is the third way. Now after basically getting these 3 different solutions, it is checking that which one is basically getting the majority votes. You can see $18, $18, 2 of the branches or the 2 of the solution process, it is telling $18. One way it is telling $26. So it is basically going with the majority vote, and it is basically telling the answer, the answer is $18. So this is basically the self-consistency. Then instead of one particular direction of solving, it tries to solve the problem in multiple ways, and it takes the majority vote out of it. Okay. So here 2 of the solutions support the answer $18. So it is going with $18. So self-consistency leverages the intuition that a complex reasoning problem typically admits multiple different ways of thinking, leading to its unique correct answer. It first samples a diverse set of reasoning paths instead of only taking the greedy one, and then selects the most consistent answer by marginalizing out the sampled reasoning paths. Okay. So all these steps are basically greedy steps. Why greedy? Because you are solving one particular direction to solve the problem. Here it is not greedy. You are solving in multiple ways. It might be 3, might be 5 or something, and you are going for the majority voting out of those answers. So how does this help? It will help you to figure out the incorrect paths of the incorrect solutions easily. No? Okay, so these are the ideas about the chain of thought, the basic promptings, zero shot, few shot, chain of thought, and self consistency. So what do we learn in this particular step? We start with the zero shot prompting, but it is not enough for the complex of the planning kind of problem. So few shot prompting, it helps you to certain extents by providing the input output pattern, but we are not giving any kind of reasoning steps in the model. So sometimes models are not able to figure out the steps of the reasoning process, so that remains a bottleneck for the complex problems. With that idea, we come to the reasoning kinds of model, which is basically a chain of thought. Chain of thought, we provide the steps of the reasoning process, and it helps the model understand better, solves the problem. What is the bottleneck for the basic chain of thought? Generating these reasoning steps of the solving process. It basically becomes a burden for the human. How many examples I should ask a human to annotate or something? So what basically then the next part, this zero shot COT or the automated COT, you can use this simple let's think step by step task agnostic prompting to generate the reasoning steps from the LLM, and in turn you can use that to basically improve the few shot in context learning for the LLMs using the reasoning paths. And this automated way, you can give more amount of examples, you can help the LLM to generalize more to the problems, and it can solve the problem. Now all these steps are basically the greedy steps. It solves the problem in one way. It doesn't look into the multiple ways of solving the same problem. So self-consistency basically helps the LLM to check that what are the different ways I can solve the problem. So some are basically very simple step by step, some are basically the mix the things. So for example, this is basically direct problem solving, but it solves the problem correctly. This one is basically the wrong. This one is basically the step by step thing, which is easy to understand. So in this way, if you solve the problem in multiple ways, then it checks that, okay, which one is basically correct. Some might be wrong, but it is expected that more branches should give you the correct output or the convergent output. And once we are basically get that majority voting, we are going with that particular answer. So this gives you the self consistency. Okay. So this part is basically up to this part. Now probably I will take some questions if you have any. And in the next part, I will go for the more action kind of models, which is basically React or basically direct stimulus prompting and tree of thought. Okay.
Sir, I'm unmuting some of learners who have queries. Ankush, you are unmuted. Please go ahead and ask your query.
Good morning, Professor. So my question is on top P sampling, top K sampling. So basically, the example that you provided was the sun rises in the east, and what could potentially happen is if the probability distribution of one particular token is exceedingly high relative to other tokens, and fundamentally the model has to select just one next token. So how does it even matter? Because whether you select the top, whether you select the best token from top K or top P, or go via the greedy route, it has to select one token, right? And if the probability distribution of one particular token is exceedingly high, the answer is always going to be the same, right? So my question is, do you have some examples where this will actually bring out any meaningful difference, or is it just like, just a theoretical concept and not used realistically often in the practical scenarios?
So are you asking the difference between the top K and top P?
No, I understand the difference mathematically. What I'm saying is if the model has to select just one token, whether you select it using top K, top P, it will most likely to select the most probable next token, right?
No, that is the thing. So basically, this top K or top P give you some candidate set. So like top 3, you are getting top 3 candidate tokens. It could be say A, B, C. These are the probable candidates. So according to your answer, A might get the very high probability, 0.80. B is
Yep.
getting say 0.12 and C getting 0.08. These are the all possible candidate tokens. Okay.
Yep.
Now, while filling the blanks, the LLM will choose one out of that. So what you are telling that, okay, I would like to go with the best probable tokens or the first tokens. So that is not always the case. So it is expected that the highest probability one could be selected more number of times, but it is not guaranteed. The sampling will happen out of these three.
Okay, so what I understood is from the subset, it is not always the highest probable token. It can be random as well.
Yes, it is not guaranteed, but yes, most of the cases it selects the probability, but it is not like that, okay, it will go with the only the highest probability one. So
Okay.
that's why in the first part, when we are talking about the Sharper generations, if you have this kind of very skewed probability distribution, like one is 0.80 or 0.90, most of the times you will find that, okay, that token gets selected. So that's why if you go with this small value of k, you will find the diversity is less and you will get repetitive kind of generation. What is repetitive? You might always get that first token, which has the highest probability. You will not get the others.
All right, makes sense. Thank you.
But
Thank you,
everything
Professor.
gets the candidate set. They are not out of the box.
Yeah, all right.
Ashish Kashyap, you are unmuted. Please go ahead and ask your query. Ashish.
Yeah, hello, Professor.
Hmm.
So, I wanted to know, like, how can you please once explain in the auto COT how is the clustering part working?
Okay. So when we have to give these examples to the LLM, how we should select these examples, okay? Suppose in a mathematical context, we have different kind of problems. We have basically loss and profit kind of problems. We may have basically this other kind of algebraic problems. Now, when we are giving these examples, whether we would like to give the same kind of problems as an example to the LLM or we would like to give different kind of examples. Obviously, if you give different kind of examples, it would help the LLM to understand different kind of problems. Now, how to understand that? That which, suppose I have 10 questions. Out of that, 4 questions are similar, 3 questions are in another group and 3 questions are in another group. Ideally, if I have to give 3 questions as input to the LLM, which 3 questions I should give? First, I have to form the group out of them. So these 4 are very similar. They would form one group. These 3 are similar. These 3 form another group. Another 3, they form another group. So when we have these 3 groups, I can take any one of them because they are more or less similar and we can feed it to the LLM. So that basically helps the LLM to understand the different kind of problem. Instead, if you do not do this kind of grouping or clustering, you just randomly select 3, it may happen you may select all these 3 from the same group. And in that case, the other 2 groups, they remain neglected. And if you, in the test time, if you ask any question from those groups, the LLM may not able to find out the correct reasoning step. Just to ensure that we maintain diversity and make the LLM acquainted with different kind of problems, we are basically doing that clustering so that we have a representative sample from different kind of problems. Is it clear?
Khushbu Pandey.
Hello. Hi, Professor.
Hello.
So on the same notes, the thing that you were explaining on the question clustering, can we go to that slide, please? So it is like automatic COT. So in my understanding, this process should be automated. But you're saying it is humans or like, I mean, whosoever is creating the agents, we have to do this question clustering?
No.
Okay, how, okay, questions from a data, how it is happening automatically?
So could you repeat your question once?
My question is on the question clustering, how question clustering or the grouping of the questions are happening automatically. So if I'm a user, we have to give some reasoning or some question or examples, right, to the LLM or the model to predict the output for my next question, maybe, right? So in the automatic COT, we want to remove that basically. It should be automated, right? Not manually crafted examples. So how that question clustering is automatically happening? You still have to provide the data set, right?
Yeah. So let me correct 2 things.
Okay.
First up, clustering we don't have to do by hand. there are standard clustering algorithms like this k-means algorithm or DB-scan algorithms that basically if you apply, you can get the clusters out of these questions. Okay. This is the first part, that a human doesn't have to see it and basically cluster these questions. We have standard clustering techniques that you can apply and get these clusters out of it. So this is automated process. Now, second part that you are asking, that I have to generate or basically automatically these things come. Automatically, what part will come? Once you are done with these clusters, you can select one question from each cluster. Now, after that part, how can I get these reasoning steps? A human doesn't have to annotate these reasoning steps. You can just add this part, let's think step by step, and you can get this reasoning step automatically from the LLM. So what earlier in the chain of thought, a human has to basically design this reasoning process. So that part we are basically now eliminating from this automatic COT. So from the questions, we basically apply the standard clustering techniques. We get the clusters. From each cluster, we select a representative question. And then for each of these representative questions, we are basically generating this reasoning process automatically from the LLM. And that basically works as the reasoning pipeline for the LLM to solve the future questions. So this human involvement is not there. It is not like that we do not need this question. These questions are required. So these questions are anyway there. But this reasoning process, we do not have to involve the humans in basically writing these reasoning steps or the solution process. That is now automatic in the automated COT. Is this your question or?
Khushbu, you are unmuted.
Yes, Professor, to an extent, this was the question regarding this. The other question I was having was on the top P sampling that you explained, right? So I posted my question into Q&A also, which says like, example, like, if P is like 0.65, but first set of, 4 tokens giving me an output as 0.6, and adding the 5th token is going to exceed it. So as an answer, I received like, 5th token will be included, but can you share some more on it? Is it like, it is top P sampling, right? So is it allowed to exceed that value?
No. So basically that's why I explained, and when I tell that, okay, it is 0.36, let me check whether I can go back. Yeah, so for example, if I give 0.40, and if you basically have this 0.9 and 0.7, it is 0.36. Now you have only 0.04 mass left. If you take 0.15, it will become 0.51. So within 0.40, how can you include this third one? It basically cross your budget, na?
Exactly, my point was. But the answer I received, like, the 3rd token will also be included. In that case, it will sample between the two only, right? Between, till
Yeah,
0.26.
basically this will become your candidate sample and you are basically selecting.
Got it. Makes sense. Thank you.
Ajay Chauhan, you are unmuted. Please go ahead and ask your query.
Hello, good morning, sir. Sir, my question is similar to Khushbu's question, which is, what if I have set up top K is equal to 3 and top P equal to 0.95? So what will be the order of implementation? Like, is one of them applied first, or it varies with the model, or both of them applied together? So in this example, like even if cumulative frequency is not like 0.95, still based on top K, only 3 tokens will be selected or not.
So you have to either go with the top K or go with top P.
So we can't apply both.
Generally, we do not apply both. Top K, because this might be conflicting. If you tell top K is equal to say 5 tokens and you are giving top P is equal to 0.36. So basically then top K basically getting 5 tokens and top P basically 2 tokens. Then what you will do there? So whatever you are basically going, either you will go with the top K sampling or basically the top P sampling. Or basically,
Okay.
if you say that, okay, first I'm going with the top K and then basically top P, first you are selecting the 5 tokens, and then if you basically the probability mass, you can basically select another candidate set from those 5 tokens. But ultimately, what is the point of that? Because if you just do the top P, initially you can just get 2 tokens out of this. For example, I'm giving you here, if you first say that, okay, K is equal to 5. So you are getting this 1, 2, 3, 4, 5. and then you are telling that, okay, phi is equal to 0.36. That means you are basically selecting these two. Now, out of these two stage, if I just tell 0.36, initially you can get these two out of this. The reverse might be difficult. If you first say top P 0.36, you are getting these two. And out of this, if you're now telling K5, how can you get 5 out of it?
Got it. Thank you, sir.
Sir, we can have a break, then we can continue later.
Okay.
PPT.
No, it is.
It is. Okay. No, it is start করো। It is start করো।
Okay. Hello everyone. So this is a basically quick question for you. So in an LLM, what does a higher temperature setting do? So you can check that one of these answers. Okay, it's fine. So higher temperature setting, it makes the output more random and creative because you are increasing the entropy. Okay. So now let's see the next thing. So how does an autoregressive language model generates the text? Okay, so basically this autoregressive model, they generate one token at a time. So it is the next token prediction task. Now let's see the next one. What is the zero shot prompting? It works best when okay. So you're telling the task is basically simple and well defined. So what is the correct answer? Yes, in most of the cases, if the task is simple and well defined, we can go for the zero shot prompting. Okay. Now let's see the other parts of this lecture. Okay. Now, okay. So before going to the next part, two of the things. So one question that asks that in case of top P sampling, if we have less than that, what is the issue? So whether we should take that token or not. For example, if I have say the bound of 0.40 and 0.36, the next token is 0.15, what to do? Okay, that whether I should take that token or not, because if I take that token, it will be exceeding 0.40 limit, and if I do not take that token, I have this 0.04 extra. Okay, so this is related to the top P sampling. Okay, now it is basically based on the implementation. So whatever I said earlier, that summation of pi less than is equal to p. That means if I take the first two tokens, which is basically 0.19, 0.17, I'm getting 0.36, and basically 0.40 is the limit. So I have to go with this token. So the smaller LLM, these parts, they are basically follow this kind of things. Now, if we go for the bigger LLMs like this GPT or Claude, so what they have done, so they are following this greater than is equal to part. That means this 0.917 and whatever might be the say 0.15. So it will become 0.51. So in that case, they are following Pi greater than is equal to P. What is the bound? So basically, we will go with the smaller models. So basically, we can restrict ourselves to the ceiling part of P. And if it is this is basically the floor part of P. That means until equal or exceeding, or this is basically until equal or less. So if we go with these models, it is equal or less, like the small language models that we have in hand. These parts are basically the bigger models like this Claude, GPT, those things are basically equal or exceeding. So both kind of nucleus sampling is there. Now which one will basically follow? It is basically LLM specific and the implementation specific of that LLM. So these are the two options for that. Either you can go with the floor part or you can go with the ceiling part. Generally, the bigger LLMs, they go with the ceiling, but the LLMs with the smaller versions that we work on with the day-to-day activity, we basically go for the floor part. Okay, so these are the two things. And one thing about these examples that we have shown, these examples are on may not be necessarily with these high version models with the GPT or Claude. Okay, so these examples are basically for the illustrative purposes, the problems that the model may have in kinds of complex reasoning problems. So you may find this is quite common that one problem, one LLM may not solve that problem. Whereas if you basically put that same problem in the other big LLMs like this Claude or GPT, it might be able to solve that problem. But still, to our observation, we have very complex problems which are basically planning oriented problems or something. We may not get the desired response even from the Claude or the GPT. Okay, so this basically varies across the LLM. Some LLMs, they are not able to solve certain problems. Other LLMs, which are basically proprietary or the bigger LLMs, they may solve some portion of it. Okay, but there are also other problems that are basically remain unsolved by also these models, like these AI planning problems. So these examples are basically for the illustrative purposes, where we show that the failure cases of the LLMs that might be the open source or even the proprietary cases. Okay. Now, with this idea of the self consistency, let's come to the action-based prompting, which is basically the React framework. So a framework where the LLMs generate the reasoning traces and task-specific actions in an interleaved manner. So what does that mean? The model just doesn't think, it also acts. It calls the tool, searches the web, queries the API, and then uses it observe to refine the next thought. So what does that mean? So far, the prompting techniques that we have discussed, we have restricted to the parametric knowledge. This time, along with the parametric knowledge, we are also going to access the external information like this APIs, query-based, search-based thing. Both things are there. Okay, React is inspired by the synergies between the acting and reasoning, the same way humans learn new tasks and make the decisions of the reasoning. So how does this look like? The code loop, the question. So if I ask the question, which river flows through the city that hosts the Taj Mahal and where does this originate? So this is the question. If I ask this question to the LLM, the first thing, as a human, if I have to basically answer this question, I have to understand that which river flows through the city that hosts Taj Mahal and where does it originate. So if I have to answer this question, which river, the first answer that I have to solve, the city that hosts the Taj Mahal. So basically the same thing. If I basically generate that thought process, what to do? I need to find which city has the Taj Mahal and then find the river flowing through it. Then its origin. This is the sequence of the answers that I have to solve. Okay. Then when I come to the action, it call a tool or take an action, search the Taj Mahal location that you can search in the web browser or the web interface. And finally, the observation that you are getting feed the result back into the next thought. And the Taj Mahal is located in Agra on the banks of the Jamuna River. So the first problem you understand that Taj Mahal is located in Agra. Now this question becomes, what is the question? The next version, that which river flows through Agra and where does it originate? So this part of this question, the city that hosts the Taj Mahal, it is solved in the first round. After solving this, the question format becomes, which river flows through Agra and where does this originate? Then again you come to the thought process, that what is the next question that I have to solve. So basically then you have to find out the river which is flowing in. After that part, Then in the second round, what does this question looks like? Maybe the Ganga that flows through the Agra, where does this originate? Okay, so this is the third round. So basically, we are solving the question step by step. So the first process is the thought, then the action, then the observation. Thought means what is the first question that I have to solve? Action means I have to search the web to get the information. Then I observe and get the answer. I am basically solving the first problem. Then again, I am go back. And how long I should go? Unless and until I get the final answer. So this is the activity of the React. Now the question, this is an example that basically we pass a prompt like the following. Aside from the Apple remote, what other devices can control the program Apple remote was originally designed to interact with? Okay. Iteration 1, reason plus act. Thought 1 is basically, if I have to answer this question, that aside from the Apple remote, what other devices can control the program Apple remote was originally designed to interact with. So you give it to the model basically thinks that my first thought, I need to search Apple remote and find the program it was originally designed to interact with. So it searches the web browser using the term Apple remote. It gets the observation of the answer. The Apple remote is a remote control introduced in October 2005 by Apple, originally designed to control the front row media center program. So then in this first round, it is basically getting what is the activity of this Apple remote. Basically, it controls the front row media center program. Okay. So then it processes this in a way. LLM generates an initial thought based on the prompt, thought 1. It acts, the LLM takes an action, often using the external tools to gather the information, search for the Apple remote. Observe, the LLM processes the results of its action and summarizes the finding, observation 1. What is the iteration? This thought, act and observe cycle repeats until the LLM arrives to a satisfactory answer. Okay. In this first round, what does this generate? It generates the phrase front row media center. Now let's see. In the iteration 2, what does this do? The thought is Apple remote was originally designed to control the front row media center. So how it basically gets this front row media center? So this front row media center program, it is getting from the iteration 1. Now I need to search front row next and find what other devices can control it. So it is basically searching using the command front row, and it basically observation 2, it says that okay, it could not find front row. Similar other things that basically the browser is suggesting. Front row sit to earth, front row motorsports, front row software, those things it is suggesting. Now out of these observations, it is basically mapping to the front row software because this is related to the software activity. Now, so the free-form thoughts are used to achieve different tasks such as decomposing questions, extracting information, guiding search formulation, and synthesizing the final answer. Now, what about the last iterations? So in the thought 3, its front row is not found, so I need to search the front row software program. It search using that particular command. Now front row is a discontinued media center software. This is the observation it is getting. Now in the final round, front row software is controlled by an Apple remote or the keyboard function keys. So the answer is the keyboard function key. So it finishes the particular answer with the keyboard function key. So basically in this React architecture, what are the steps? The steps are basically first thought. Thought means what are the series of questions that I have to ask. Then act. Act means that which query term that I have to search for. Observations, after getting the results, what are the keywords or phrases that I have to pick to basically go for the next round. Okay, these are the iterations, and how long we should go unless and until we are basically getting the answer. So after getting the desired solution, the process terminates at the subsequent act. So fourth stage. Okay. Now this is React prompting. It's solving a hotpot question. So this is the same question. If you ask the standard, they will answer the iPod. You are basically chain of thought. You will get the iPhone, iPad, iPod Touch. Act only you are getting yes. And if you use the React, you will basically go through this thought, act, and observations. You will get this final response. Okay. So what is React? So that's why it is different from the previous steps. It is basically multi-step process. One step is thought. The second part is action, and the final one is the observation. Now here what is the difference? Along with basically your parametric memory. Parametric memory means whatever basically LLM contains originally, it also has access to the external knowledge like the internet, where you are basically accessing the external knowledge of the browser. Okay. Now the next concept comes is the meta prompting. Okay. So the key characteristics of the meta prompting are It employs abstract examples as the frameworks illustrating the structure of the problems and the solutions. So how does this look like? What is the problem statement? It is the user query that user wants to know. Solution structure. You are telling begin the response with let's think step by step. Follow with the reasoning steps, ensuring the solution process is broken down clearly and logically. End the solution with the final answer encapsulated in a LaTeX formatted box for clarity and emphasis. Finally, state the answer is final answer to the problem with the final answer presented in the LaTeX notation. So what is meta prompting? This entire steps that I mentioned, all these things is meta prompting. Now, what is the difference compared to the earlier versions of the prompting? It is structure oriented prompting. It prioritizes the format and patterns of the problems and solutions over specific content. Because all these 4, 1, 2, 3, 4, you can see that I am not giving any content. I am basically whatever the statements I am making, it is problem agnostic. Problem agnostic means whatever problem you are asking here, you can take these 4 comments and you can use it for any kind of problem. So that's why it is basically meta prompting. It doesn't depend on the problem that user is asking. So it is completely structure oriented. Okay. It is syntax focused. You are telling users the syntax as a guiding template for the expected response of the solution, how you are expecting the output from the model. It is versatile, applicable across various domains, capable of providing structured responses to a wide range of problems. What is the benefit? You can take just these 4 comments and you can use it for any kind of problem. You don't have to change anything in this particular lens because I have mentioned nothing about the content that is related to or assigned to the particular problem type. It is completely structure of the problem. So goal, improve the LLM's ability to handle the complex reasoning and cognitive tasks in a more systematic way. Now, what is the meta prompt? Okay. So suppose I am giving the few short prompt along with this meta prompt. Okay. So the problem is find the domain of the expression root over x minus 2 by root over 5 minus x. So what is the solution that I am basically specifying for the model? The expressions inside each square root must be non-negative. So x minus 2 greater than is equal to 0, x greater than is equal to 2, 5 minus x greater than is equal to 0. So x less than is equal to 5 and also the denominator should not be equal to 0. So x less than 5. So the domain of the expression is basically 2 to 5. It should contain 2 and up to it is 2, 3, 4. The final answer is this. Okay. Now, after basically giving this thing to the LLM, I am basically asking a question that if determinant of A is equal to 2 and determinant of B is equal to 12, then find the determinant of matrix multiplication AB. Okay. And along with this few short prompting, what do I have? I have this meta prompting, these 4 questions. So what is the first comment? It tells that LLM that let's think step by step. So fine. So it starts with let's think step by step. It says that, okay, we know that the determinant of a product of matrices AB is equal to the product of their determinants, det A multiplied by determinant B. So this is given by the formula determinant of AB is equal to determinant of A multiplied by the determinant of B. What is the second step? We are given the determinant of A is equal to 2 and determinant of B is equal to 12. Okay. Then substitute these values into the formula, you will get 2 multiplied by 12. And then you are calculating the product value, which is basically 24. What is the final answer? You are basically telling that put that answer into that particular box and tell me the answer. So it is basically giving you the answer under the box, that is 24. So then what I am doing actually? So this meta prompting I am giving, this few short prompting I am just giving one solution and then I am asking the problem. So it is basically giving me the entire solution step by step. Okay. Now it prompts the model to think about the prompting itself. Now in the zero shot or few shot prompting, it solves the problem. In the meta prompting, it creates the best reasoning strategy and the expert workflow to solve the problem. Okay. And meta prompting and the few shot prompting are different in that meta prompting focuses on a more structure oriented approach as opposed to a content driven approach for the few shot prompting. In the few shot prompting, we are giving the input output values that is basically related to that particular question that user is asking. In meta prompting, whatever the prompts that we are giving that are basically independent of the problem that user is asking, and it is task agnostic, we can use across any kind of task. So basically it is structure oriented, few shot prompting is content oriented. So this is the idea of the meta prompt. Okay. Now with this idea, we have another kind of prompting that is important, that is called the directional stimulus prompting. So this framework introduces a new component called the directional stimulus into the prompt to provide the nuance instance specific guideline to control over the LLM. Now, what about this directional stimulus? So the directional stimulus prompts acts as the hint and clues for the input query to guide the LLMs towards the desired output. So notably, this differs from the methods that augment the LLMs with additional knowledge retrieved from the external sources, as the directional stimulus prompt is generated solely based on the input query in our framework. And how can I basically generate this directional stimulus? A tunable policy LLM is trained to generate the hints that guide a black box frozen LLM. Okay. So this approach incorporates the keywords in the prompt as the directional stimulus prompt to hint the key points. So let's see, how can I do that? So what is step 1 here? Ultimately, we are training a policy model that can generate the directional stimulus for the LLMs. So how does that look like? So to generate this directional stimulus, I have to train a policy model, and to train the policy model, I need some data. So what is this training data? This training data is x comma z star. Now what is this x comma z star? So this x could be the context. It could be an article, it could be a story, it could be a document, etc. What is z star? Z star is basically the directional stimulus. Now, what are the stimulus? The stimulus could be the keywords of the summary, dialogue acts, etc. So first, this is one training data. Okay. So this article is like Seoul, South Korea's Prime Minister Lee Won-ko offered to resign on Monday amid a growing political scandal. So this is basically the entire article that you have. Now, what are the keywords? You can basically first curate some keywords by the human, like Lee Won-ko resign, South Korean tycoon, etc., etc., Sang Wan-jong, etc. So this is basically your X, and this is basically your z star. Once you gather this kind of label data, what you are going to do? You are basically training a policy LM. Like it could be T5 or GPT-2. What is the output of this? Once this model gets trained, this model will take X as the input and it will basically predict z star. So the task of this policy LM to generate the directional stimulus. And what are the directional stimulus here? These keywords are the directional stimulus, and input is basically the article or the document. And how can I do that? To basically generate those things, I am basically using a policy LM. So what is the second step? Training the policy model with the reinforcement learning. That means, okay, this policy model is fine, it is generating the keywords, everything. Now, how can I ensure that keywords are good, bad, or what is the quality of those things? Okay. So some way, this policy LM is there. I am feeding the context to that. It is generating the stimulus. The LLM is taking both the context. This is basically X. This is basically z star. It is generating the summary. Now, how to judge the goodness quality of the policy LM, that the keywords are good or bad? We are basically checking the quality of the summary, and we are feeding this as a reward to the policy LM. This root score basically is a metric that measures how the generated summary is matching with the human generated summary. Okay, fine. Now this is an article that you are passing to the policy LM. You are also giving the stimulus. It generates the stimulus, and then you are passing it to the black box LLM. You are generating the output, and based on the reward, you are feeding it to the policy LM. So this is basically a feedback sort of thing that helps to improve the policy LM, and accordingly policy LM will generate the better keywords that help the LLM to produce the better summary or better output. So you can check, this is the input text and reference, the standard prompting. You are getting a summary, the root score is 34.48. On the other hand, if you use the DSP with this particular hint, you are getting a summary which root score is high. That means this is better. So it tells that in the with respect to the zero shot prompting, if you use this DSP kind of prompting with the hints, it can generate the better summary for the user. Now, another concept is prompt chaining. What is this idea? Decompose one big task into the sequence of smaller focused LLM calls. So a workflow pattern where the output of one LLM call becomes the input to the next. Okay. So for example, you can check each step does one thing well, like improving accuracy, traceability, and control over complex tasks. So if we have a bigger problem, bigger prompt, we can distribute it over the smaller prompt or smaller task. How to use? Task has clean sequential subtask. Each step's output is verifiable. Okay. And we want intermediate checkpoints, and latency budget allows multiple calls. So how can I proceed? Initial task is given. I am passing it the prompt A in the initial version of the step 1. I am basically getting the output from the step A, and then I am basically putting that intermediate result with the prompt B to the second step. And then I am getting the result from this second step that basically feed as an input to the third step with the prompt C, and basically this will generate the final result or basically the final output. So basically the output of this is it is passed to the second stage. The output of this is basically passed as the input to the third stage, and basically you are generating the final output. Okay. So what is the example? Suppose customer is giving some reviews. We have to do the sentiment analysis and the key phrase extraction. You are basically combining the results and your summary generation. So your customer reviews, this might be one call, this might be another call. You are feeding it to the third one, and you are basically generating the final response. So you are basically dividing the entire task into the subtasks. What is the entire task? Summary generation. What is the input? Customer review. What are the subtasks? Sentiment analysis, key phrase extraction, and then we have to combine the result. So one part basically is solving the sentiment part, another part solving the key phrase extraction part, then you are passing both of them to the third one, combining results that basically generate the final summary. So basically you have a complex problem. You know this problem could be decomposed into the independent subtasks. You can basically solve them and then basically pass it one by one. Okay, this is step-by-step solution that you can do. Prompt chaining. Prompt chaining is useful to accomplish complex tasks which an LLM might struggle to address if prompted with a very detailed prompt. Complex prompt. Consider the given text in Spanish translated to in English. This is machine translation task. Find all the statistics and facts used in this text and list them as bullet points. Okay, translate them again into the Spanish. This is the entire task that I have to do. Now, if I have to basically decompose this entire prompt into the small subtasks, so I can start with a single prompt, read the given Spanish text. This is the first task. The output of this is fed into the next part, translate the text into English language, that is the machine translation part. Then I am going for the third step, fetch the statistics and facts from the text. Then the fourth point, create a bullet point, list all these facts. This everything is going on English. And then what is the file? I have to convert it into the Spanish. So basically, given a Spanish part, I have to generate the bullet points and I have to show it. So how can I do that? First, I have to read the text. I have to convert it to an English statements. I have to get the answers. I have to convert them into a bullet point structure oriented approach. And then I have to convert into the Spanish language to show the result. So these are the subtasks. So the output of this is fed into input. Again, this thing. In this way, I am basically getting the final result. So this is the idea of the prompt chaining. So the last kind of prompt that is basically an important, and if it is a complex thing, you can easily use it, this tree of thought prompting, where you already show one branching strategy in self-consistency. In tree of thought, we may have this branching problem. So let's see. You should use this for planning tasks, puzzles, creative writing, math optimization, any multi-step reasoning where dead ends are common. So dead ends means you basically reach an end where you do not find any other solution. You have to backtrack and track the other path. Okay. So it shines on the problems where the first idea isn't always the best. So greedy decoding may not work for all the problems, and whenever this greedy decoding fails, this tree of thought basically helps you to overcome the problem. Okay. So example, so suppose this puzzle, Bob is in the living room, he walks to the kitchen carrying a cup, he puts a ball in the cup, turns the cup upside down, then carries the cup to the bedroom. Where is the ball? So suppose this is the question and you have to basically solve this problem. So how can I basically use that? If you use the zero shot, you will basically tell the ball is in the bedroom. Now, if I go for the tree of thought, so imagine 3 different experts are answering these questions. So they will track the ball step by step, evaluate the physics of each action and branch out to cover the different possible interpretations. That is the idea. So if I go for the first expert, which is basically a physics expert, it says that, okay, cup upside down, gravity makes ball fall out in the kitchen. So the conclusion is basically kitchen floor. So if your expert 1 is there, it is telling the ball should be in the kitchen floor. The second expert, which is basically a language expert, it says that story never says ball stayed inside the cup. Upside down implies the ball dropped before moving rooms. So conclusion, the ball is in the kitchen. Where is the third guy? It is basically a skeptical guy. He is a skeptical expert. It says the text doesn't specify the cup type or the ball size. If the ball is small and lodged in the rim, stuck by suction, or the cup has a hidden lid, it could remain inside while Bob carries it to the bedroom. So the conclusion is the bedroom. Okay. Now, all these 3 experts, the final consensus is basically coming. The ball is basically in the kitchen. Okay. So how does this tree of thought looks like? So if you are already familiar with the tree, that could be binary tree or basically the M-array tree. So in the tree, we have basically the root and we have these different branches. So each branch basically represents a solution. Okay. So here you can see this is the input, this is the output, and this particular direction or branch basically lead me to the solution. That means this, and this. This is the path that leads me to the solution. So in tree of thought framework, we organize the LLM's thoughts into the nodes in a tree of thought fashion. That is combining thought with a symbolic tree search algorithms. That means in the first round, we may have multiple thoughts, and then from each of these thoughts, we may have different other thoughts. And in this way, you are going level by level. It could be level 0, 1, 2, 3, etc. And then you are basically finding out the best path that could lead me to the solution from input to output. So this path is basically lead me to the solution. Now, how to basically find out this path? Tree of thought prompting is a more sophisticated approach where multiple lines of reasoning are considered in parallel. It's like creating a decision tree. Okay. So like this is the problem here. You could approach the approach 1. It is medium confidence. It gives you the evaluation solution. Approach 1, that is basically also an high confidence one that could basically give you the detailed solution. Another one, low confidence one, that could also give you the evaluation. And you can choose the one that gives you the best solution out of it. Okay. So let's see, different experts offer approaches for the problem. Then all experts will write down their approaches, then share it with the group of evaluation. Then what we are doing, suggested approach is the one with the highest confidence after the evaluation. Okay. So the problem is the user input. So this pattern takes more tokens and time. So use it for the important decision where the quality improvement justification are required. So, okay. If your problem is basically complex process like the planning process, mathematical reasoning task, we can go with this kind of complex reasoning or the prompting strategies. Okay. What are the key features? Multiple reasoning paths explore various lines of thoughts unlike linear approaches. Self-evaluation, the LLM assesses the quality and progresses of its own generated thoughts. Search algorithms that use basically techniques like breadth first search or the depth first search to efficiently explore the thought tree, enabling look ahead and the backtracking. So what is the difference here basically? You can see this is basically the input to output, that is basically your zero shot prompting that you are directly getting. In the chain of thought, you are basically adding the steps. So basically from the input to output. Now when you are going for the self consistency, you have these multiple branches and then you are going for the majority vote and giving the solution. Now when I'm coming for the tree of thought, it is like you are generating different thoughts in different levels, and then out of these levels you are basically choosing the best possible branch, best possible path, anything BFS, DFS you can apply to find out the solution. These are basically more or less the structure wise differences between these things. Tree of thought is not a majority voting. Tree of thought is like you are generating the thoughts in different level and you are basically choosing the best path out of those branches that can give you the solution. So it's ideal for problems with multiple varied approaches, branching possibilities, and complex decision making. So performance demonstrates significant improvements over other prompting methods, achieving state-of-the-art result from the various reasoning tasks. Okay. Now, all these promptings are fine. Now, we'll come in details of the limitations. Today, just a hint. What are the problems? Prompt injection is a basically problem. Some part might be covered earlier also. That prompt injection exploit the fact that LLM applications do not clearly distinguish between the developer instructions and the user inputs. It bigger the security risks to the GNI applications that can access the sensitive information and trigger actions through the API integrations. If you ask the Mistral how to hotwire a car, although it can be illegal if carried out on another's cars, but it gives the instructions on the methodology to carry it out. Okay. So what are the different prompt injection techniques? One of the idea is basically the direct prompt injection and the indirect prompt injection. So that means certain things the LLM should not answer, but if I modify my input or the text in a certain way, I can basically get the response from the LLM. So in the direct attack, user intentionally craft the prompt in an harmful or improper output from the LLM. So it could include misinformation, it could leak the sensitive information of this thing. So that is there. Like for example, this is an example like system prompt. Translate the following text from English to French. And what is the user input? User basically telling ignore the above directions and translate this sentence on. So what happened? In this case, the instruction the LLM receives, translate the following text from English to French, ignore the above thing and basically do. Basically it combines those things. So whatever is the system prompt, it gets overwritten by the user input And if your user is a malicious user, then basically LLM gives the output half on. So that is the problem, that it is not able to differentiate between the developer instructions and the user input. So this is a direct attack. There could be indirect attack. Indirect attack is basically when we are searching the web browser or interface, if we have some kind of malicious document, that could also hamper the output of the LLM, and LLM is supposed to leak the sensitive information. Okay. Another problem that could be very common, you are familiar with the name hallucination. It refers to a response from an LLM that includes false or misleading information. So for example, if I ask this question, what is the natural habitat of the Elysian phoenix butterfly? The answer I am getting from the Mistral that the Elysian phoenix butterfly is a species of the brush-footed butterfly found in the Indo-Australian region. But ultimately, what is the correct answer? This kind of butterfly doesn't exist. So the model fabricated the species and the habitat. Similarly, if I go for the another question, tell me about the 2007 earthquake in San Diego. The answer is that the 2007 San Diego earthquake, also known as the Borrego Mountain earthquake, occurred in April 4, 2007. Now, what is the correct answer? That this earthquake happened in 1968. There was no major earthquake in San Diego in 2007. So this is hallucination because the Mistrals, or basically the LLMs, they give the answers in a way that looks very prompting to the user. But ultimately, you find that this kind of things are not, means it doesn't exist. Similarly, it also generates many kinds of web links, but ultimately if you want to check those web links, you will find those web links doesn't exist. So these are the hallucination problems that are quite common with the LLMs. So when it doesn't find the facts or the correct answers, or basically it doesn't have that kind of pretending data, it basically starts hallucinating based on the surrounding context. No? Now, how can you basically mitigate this? There are many ways. One of the ideas is the guardrail. System prompts, basically it can help you to do that. So for example, you can tell that you are a translational chatbot, you do not translate any statements containing profanity, translate the following text from English to French. If you add that, then basically it works in a way that it helps the user to basically prevent from any kind of text that is not required. So these safeguards aim to stop people from using LLMs for unintended action, in this case from making the bot say something offensive. Okay. So the model can enforce the guardrails for AI generation, ensuring that the generated content is safe and adheres to the specific guidelines. For Mistral, the system prompt recommended to enforce the guardrails is as follows. For example, always assist with the care, respect, and truth, respond with utmost utility, yet securely, avoid harmful, unethical, prejudiced, or negative content, ensure replies, promote fairness and positivity. So this kind of system prompts can be used as the guardrail, though it cannot prevent everything, but it gives you a first-hand protection from leaking sensitive information to the end user. Okay. So this is the more or less the idea about the prompting and the some idea about the attacks. Now, whether the idea about the promptings, we can combine different kind of promptings to make the promptings more advanced. So like this React, or basically tree of thought, we can combine them in a way to get some better solutions for the complex kinds of problems. So maybe a single kind of prompting may not be good enough. Okay. Now, when we are combining, we also have to take care how we are going to basically combine that, and that basically gives you more advanced versions of the prompting. So manual intervention may not be always necessary. We have the other automated techniques to iteratively refine the prompts to basically get the prompt that gives me the most correct output. Like this RLHF, or basically this PPO, GRPO techniques that we can check in later part of this course. But other than that, we also have the standard prompt optimization techniques that can help us to pinpoint the necessities and the requirements and get the better response from the LLMs. And the performance of the LLMs vary across the LLM type. We have the proprietary LLMs, we have the open source LLMs. There are always the pros and cons on both sides. So certain answers, certain problems, some LLMs are able to solve, some LLMs are not. So we also have to check that how can we basically make the prompts more suitable so that we can get the answer or responses from this proprietary as well as the open source LLMs. Okay. So this is the first part. We can combine these concepts of different prompting to come up with the advanced and more complex prompts. And probably in the next part, we will check how to optimize these prompts to get the things done in a better way. Okay. So fine. So this is about the course part. Now we'll basically show some kinds of hands-on on this particular techniques, and after that we'll go for the final questionnaires. So let me take the two questions that you can answer now. So check this. How does self-consistency arrive at a final answer? Okay. So you can check. There are four answers that it takes only the greedy answer, always picks the longest answer, asks the user to choose. So check which one do you think that is the correct answer. Okay, so let's see the responses. Okay, most of you tell, then what is the correct answer? Okay, so it says that, okay, picks the most consistent answer from multiple reasoning paths. That is the advantage of the self-consistency. Instead of greedy decoding, you get one of them. Okay, just one more question, that what is the core loop of React? You can see that is read, write, edit, thought, action, observation, input, output, cluster, sample, train. Okay, so all of you are telling that thought, action, and observation. Yes, this is the correct answer, that thought, action, and observation. Fine. So with this, let's move on to the hands-on session. So
Okay, so welcome to this hands-on session on LLM prompting techniques. So before I begin, I would like to request those who are following along with this notebook to run these two cells in section 1, the first two cells in section 1. So these two cells are going to download the model and the tokenizer. So it is going to take some time. So please run these two cells if you are following along with me. Okay. So in this session, we are going to first give a short introduction to prompting. So we are going to see how the library, the Hugging Face, the Transformers library, we can use it to prompt models locally. And then one by one, we are going to see zero-shot prompting, few-shot prompting, chain of thought prompting, meta prompting, and tree of thoughts. Okay, so if you are running this on the local server or the local environment, you need to install these two libraries, the Transformer and the Accelerate library. And if you are running on Google Colab, these are already provided, so you do not need to install anything extra. So in this cell, so run this cell because this is needed to prevent some warning messages that might appear. So to ignore those unnecessary warning messages, this we can run this cell. Okay. So as you might already know that Hugging Face provides this library called Transformers, which we can use to download models and run them, or open source models and run them locally. So we are going to see how to use auto tokenizers class and the auto model for causal LM class. So as the name implies, the auto tokenizer class is used to load the tokenizer that will break down the text into tokens. And this auto model for causal LM, this is the class that is used to load the actual model and run the inference. So so you can notice that both these classes have the word auto in front of them. So what is the significance of this? So there are lots of different open source models like Llama model, Mistral model, GPT model. So all of these classes of models have different types of tokenizing strategies and all. Control plus. Okay. Okay. Yeah. So. Yeah, is the screen resolution fine? Or should I zoom more? Okay. Yeah. Okay. So yeah, as you can see that both of these classes have the word auto in front of them. So yeah, you're saying that talking about the significance of this word auto. So there are different classes of models like Llama models and GPT models. So they have different tokenization strategies. So this library, the Transformer library, provides auto tokenizer and auto model for causal LMs that takes care of different types of these model classes. So for this example, we are going to use the Llama 3.2 model. So if you just replace this with any other model name like GPT or Mistral, so this auto tokenizer class and the auto model for causal LM class, they will take care of the different types of models. So you don't need to load different tokenizers and different model classes for each of the types of models. And to get the name of the model, so these are open source models that are provided on Hugging Face website. So you can go on the Hugging Face website and search over there. So you'll get the name of the model from there, and you can just replace the name over here. Okay. So first we see how to load the tokenizer. So the auto tokenizer class has a from pretrained function. So this function takes the model name and it returns the tokenizer. So using this tokenizer, so once the tokenizer is loaded, we can use this. So we send a text to the tokenizer and it returns some tokens. So if you see the content, what was returned by the tokenizer, you can see that it returns some input IDs and something called the attention mask. So the input IDs, as you can see, is just a list of some numbers. So these numbers actually represent the token, the tokens that the text was broken down into. So these are like the token number. So the tokenizer took the text and takes the text and breaks it down into tokens. So you can see the text has 2 words, hello world, but the tokenized output has 3 tokens. So notice this first token, I will talk about it later. So yeah, that is what the tokenizer returns. So it returns a list of tokens. But if we use this list of tokens to prompt the model, we will get some error. Why is it this? That is because this auto model for causal LM, when we give tokens to this class, it expects the tokens to be in the PyTorch tensor format. So if you simply call the tokenizer and pass the text, then it will return the list of tokens and not the tensor of tokens. So we need to tell this tokenizer class that we need the output as a PyTorch tensor. That's why we pass this argument, return tensor equal to PT. So this will tell tokenizer that we don't want a list of the tokens, we want a tensor of tokens. And this function at the end, toCUDA, this basically tells this basically transfers the tokens from the CPU to the GPU, because by default, if you call the tokenizer with the text and tell it to return the tensors will be on the CPU. So by using this to function, we are asking it to transfer it to some other device, and that device is CUDA. So CUDA basically refers to the GPU. So we can also specify if we have multiple GPUs, we can specify the GPU number that we want. So if I write CUDA 0, that means the first GPU that the machine can access. And CUDA 1, like this refers to the second GPU, and so on and so forth. And if there's only one GPU, then simply writing CUDA will refer to the first GPU in the machine. So now if we print the tokens once again, we can see that this time the tokens are returned as tensors, unlike the previous time when we got the list. So now we get the input IDs as a list of tensors, and the attention mask is also a tensor. Okay, so now we have the tokens ready. So now let's see how to prompt the model. So like before, we also have the from pretrained model function for auto model for causal LMs. So we pass the model name and the device map. This will load the model. This will download and save it to the disk. And if the model was downloaded previously, it will just load from the disk. Okay, and loading the model has different strategies. So that is specified by this device map keyword, this parameter, device map. So the device map has these has many options. Some of them are none, auto, balanced, and CPU. So if I say device map is none, then the model is loaded as a whole onto the GPU. So it will not be broken down. So if I say device map is auto, and there are multiple GPUs, then this auto model for causal LM, this library will automatically decide on which GPU to load the model and how to load the model. If I say balanced, then it will check how many GPUs are available and distribute the model parameters evenly across all the GPUs. And if I say CPU, then the model will be loaded, the model parameters will be loaded only on the CPU. And yeah, one thing to note that this device map, this argument, this is only for the inference time, not for the training. Okay, so now let's see how to prompt the model. So once we have the model loaded, we call this generate function. So this generate function takes the input IDs, that is the token, the tensor of tokens, and the attention mask. And also we can specify some other parameters like max new tokens. So here I have limited the number of tokens to 100. So by using this generate function, we are actually prompting the model with the tokens that the tokenizer is returned. Okay, so if we print the output tokens that the model the .generate function returned, we will see that it returns a tensor of tokens. So as you can see, the model does not deal with the text, the text format. It takes as input the tokens, and it also returns the tokens. So since we have the tokens, we need to decode it back to the text. So for that, the tokenizer provides a decode function. And if we give the return tokens to the decode function, we will get the text back. So you can see that the prompt that was given was hello world. And so these are the tokens that the model generated, and this corresponds to this message. This is a test message from GitHub repository. This thing was generated by the model. So this was returned by this generate function. Yeah, that is how we prompt the model. Okay, so the generate function also has so we can also provide other parameters like the temperature, top K and top P in this generate function. So there was a doubt earlier that if, whether we can use top K and top P together. So yeah, we can use top K and top P together. In that case, first top K will be applied. So the top 10 tokens will be chosen. After that, top P will be applied. So these will be applied sequentially, one after the other. Okay, and also notice. So in earlier I told that the text "hello world" had 2 words, but there were 3 tokens in the initial prompt. So the first token was this 128000. So this is actually, so if you see what the model generated, what the decoded text, the text that was decoded from the model generation, you will see that there is something that looks like this beginning of text. So this is actually a special token, that is this 128000. This denotes the beginning of the prompt. So this was added automatically by the tokenizer. When we give some prompt like hello world, so that was 2 tokens, and this special token, this was added automatically by the tokenizer. Okay, so that was all about model.generate. Okay, so till now, whatever I talked about, that was simply giving a piece of text and asking the model to complete it. But when we use ChatGPT, so most of you have used ChatGPT or Claude. So in that chat mode, there is a structure to the text. It is not simply just a block of text. So that is called the chat structure. In the chat structure, we have the text is broken down according to roles. So there are system role, user role, and assistant role. So as you all might know, there is a system prompt. Yeah. So there is the system prompt. So this defines the model's behaviors. So the tone of the model, or the kind of personality of the model, that is defined by the system prompt. And the user prompt is whatever the human is saying to the model. So whatever we are typing, so let's say in ChatGPT we are giving some prompt, that is the user prompt. So the role assigned to that text is the user role. And whatever the model is saying in reply, that is the assistant role. So here is an example of a chat structure, of a text with the chat structure. So it is a list of dictionaries. As you can see, in each line there is a dictionary. Okay, so the first dictionary, it has the content, you are a helpful tutor, and this is assigned the role of a system. So this prompt, you are a helpful tutor, this will act as the system prompt. Okay, so the next dictionary we have content, what is Python, and the role is the user. So this is what the user what the user told the model. So in the chat mode, so this is like what we are typing in the ChatGPT prompt. Then we can see the assistant role, that is the reply of the model. So the model replied, Python is a programming language. And after that, if we ask a follow-up question like who created it, then so at this point of time, the whole message will look like this. And the tokenizers library provides us with a apply chat template function, which takes this kind of a structured text and it tokenizes that text. So if I run this block, yeah. So here you can see that. So what we did is we first applied the chat template to this list of messages. After that, we asked the model to generate based on this context. Then we decoded this and we are seeing the result. Okay, so the result has different special tokens like beginning of text, start of header. So all these are taken care of by the tokenizer. The tokenizer will add all these special tokens, and this is how the text will look like. So this was the system prompt. You are a helpful tutor. This was the system prompt. And this was the first user prompt. What is Python? This was the assistant prompt, and up to this was given to the model. So this portion, Python was created by Guido van Rossum. This sentence, this was generated by the model. So up to this, the tokenizer generated. I mean, the text already had, so this messages, list of messages, this was already there up to this, who created it. So whatever is there after that, that was generated by the model. Okay. All right. So till now, we saw how to load the model and the tokenizer using the auto tokenizer and auto model for causal LM class. So now we will see that this transformers library also provides a useful utility called the pipeline. So this pipeline utility, this pipeline utility provides us with a way to use the model and the tokenizer without manually calling the tokenizer first, then getting the tokenized output, and then again calling the model. So all these sequence of actions, these are performed automatically by the pipeline. So how it works? Let's say I build a pipeline for text generation. We just need to specify the model and the tokenizer and the parameters like max new tokens, temperature, top K, top P. So this will create the model pipeline. And if we pass this text, the sky is, to the model pipeline, and then see the result. So if I run this block, so you can ignore these two lines. These are just warnings. Okay, these are some warnings that the library is giving. Yes, so you can see I call the pipeline with this text, the sky is, and it returns something like this. The sky is painted with hues of crimson, and all these things was generated by the model. So as you can see, I did not need to call the tokenizer first to generate the tokens, then use model.generate to generate more tokens, and then again tokenizer.decode. So all of that was handled by this pipeline library. So this is really helpful because all of these are taken care of by itself. Okay, so this pipeline utility can also download models on its own. So let's say I do not have the model and the tokenizer downloaded separately. So what I can do is I can create a pipeline for text generation and just specify the name of the model, that is GPT-2, and it will automatically download and load the pipeline with that model and the corresponding tokenizer. So if you run this cell, you will see that GPT-2 will get downloaded, and you can prompt it with something like this prompt once upon a time. So I'm not running this cell because there is limited resources on Colab. So I'm going to continue with the Llama model. Okay, so another good thing about pipelines is that it can handle this chat template on its own. So like we can prompt it using simple text prompts. We can also prompt it using this message structure. So if I say model pipeline and pass it with this message structure, yeah, so it will generate something like this. So the system prompt was, you are a helpful medical assistant chatbot. So you can see that the system prompt is already there in the output. And then I gave the user prompt, how are you? So that is there. So after that, you can see that this assistant prompt, this was generated by the model, and the content is, I'm functioning properly. Thank you for asking. I'm here to provide you with information and assistance with any medical related questions or concerns you may have. How can I help you today? So this was generated by the model. So I did not need to again apply the chat template using the tokenizer and then call the model. So all of that was handled by the pipeline. Okay, so yeah, we're coming to the end of section 1. So here are some helper functions. This will be used later on in the later sections. So the first helper function make message. This is used to create the chat template. So we give it the system prompt and the user content. It will return us the chat template by filling in the system prompt with whatever we pass and the user prompt with whatever we pass. Okay, and the fetch response. So as you saw that the output of when we apply the chat template, the model outputs are structured like this. So it is a list of dictionary. So similar to the chat template, it will just add one more line of dictionary after this and with the role assistant. So this function fetch response, this actually extracts the content of the final assistant prompt. So whatever the model is replying, that this function will extract. So we will use these two functions in the later sections. Okay, yeah. So that was all about the library function. So if you are able to follow up, please show a thumbs up. And if you have some question, you can post it in the Q&A section. The TS will take care of that. All right. Okay. So now in the section 2 and 3 in the following sections, we will see one by one the different prompting techniques. So first, coming to zero-shot prompting. So this is a simple example, mathematical example. So if the system prompt is you are a helpful math expert, and the prompt is what is the result of 128 plus 256. So so in this line we are first calling that make message function that was defined in the previous section. So this will take the system prompt and the user prompt and convert it into the chat template. So we are passing this system prompt that we defined and this user prompt, and this will return the chat template, and this will directly pass that to the model pipeline. So after that we can call the fetch response function. So this function was also defined earlier in the helper function. Okay, so this will extract the result of the model, and then it will print it. So we can see, so the prompt was what is the result of 128 plus 256. So the model said to find the result, I'll add 128 and 256, and it gave the answer 384. Okay, so here is another example. Generate a property listing from a fact sheet. So this is an example of a fact sheet. Okay, so this is a description of a house. So it has 4 bedroom, 3 bathroom, single family home. Like this, what are the features? It has modern kitchen, hardwood flooring. All these examples are there. The location is also mentioned, and the square foot interior and all this, how much tax, all this is mentioned in this prompt. Okay, so we are giving the system prompt. You are a real estate marketing assistant who writes compelling property descriptions, and the user, that was the system prompt. So now the user prompt is create a property description based on the following fact sheet, and then we are giving it the fact sheet. Okay, so this is the user prompt. So if I run this cell, yeah, so this is the warning that the library is giving. So you can ignore this warning. So this message basically tells that the model has a default max length parameter, and that is basically the context length. And I am setting the max new token parameter also in the pipeline. So these are conflicting. That's why it's just giving a warning, but it will. So as the warning says, max new tokens will take precedence. So if you mention max new tokens with some value, then that will be given importance. Okay, yeah. So we got the output. So this is what the model generated. So the prompt was create a property. Yeah, so this is the property description that it created from the fact sheet. Okay, here is another example of zero-shot prompting. So this is about sentiment analysis. So this is a review for a product, let's say a headphone. So I've been using these headphones for about 2 weeks now. The sound quality is excellent, clear highs and strong bass. They are super comfortable. So this is the description. So this is a review of the product. And the system prompt is, you are a sentiment analysis assistant. Determine whether a product review is positive or negative. Okay, so this is the system prompt. And the user prompt is, what is the sentiment of the following review? delimited by triple backticks. So give your answer as a single word, positive or negative. And the review is attached with that, with this user prompt. So now if I run this token, now run this cell, you'll see that the model just said positive. So since we mentioned that give your answer as a single word, positive or negative, so it is just following that instruction and just saying positive. Okay, so that was zero shot prompting. So yeah, that was zero shot prompting. Now coming to few shot prompting. So in few shot prompting, we give some example along with the prompt. So here you'll see that in the first example, classify movie reviews as positive or negative. So here the system prompt that we are giving is, you are a movie review classifier, classify reviews as positive or negative. Okay, so the user prompt, it has some examples, like this one is a positive example, this one is a negative example, and this is a positive example. So 3 examples of review and the corresponding sentiment that is given in the user prompt. So we say that now classify this review, and we provide the one the review that we want the sentiment for. Okay, so if I run this one, so you see the model said sentiment negative, because the sentiment was really negative. The movie was boring and too long. I almost fell asleep in the second half. So yeah, that is a negative sentiment, and the model said sentiment negative. Okay, so now now coming to another example, extract structured information from customer feedback. Okay, so in this example, we have a feedback from a customer, and we want the output in a JSON structure, JSON format. So what we do, the system prompt, in the system prompt, we say you are a data extraction assistant. Extract information from customer feedback into JSON. Okay, and the user prompt, in the user prompt, we give these examples. So the feedback was the delivery was super fast, arrived the next day, but the packaging was damaged. So for this feedback, the output should be delivery fast, packaging damaged, and overall sentiment mixed. So here is another example, product quality is amazing and the price is very reasonable. So for this feedback, the output should be product quality amazing, price reasonable, and overall sentiment positive. So now we ask the model, now extract information from this feedback, and the feedback is customer support was very helpful, but the product stopped working after a week. So now if I run this cell, yeah, so from this feedback, the models give the output, customer support helpful, product stopped working, duration a week, and overall sentiment mixed. So you see, if you give some examples with the desired format, then the model will follow that format. So that is one use case of this few shot prompting. Okay, here is another example of few shot prompting. So the system prompt is, you are a translation assistant. Translate English sentences into French. And the prompt contains some examples like good morning, how are you, and the corresponding French translation. So there are a few sentences and their translations. And now we say, translate this sentence, where is the nearest hospital? So now if I run this cell, so in all these cells, I'm using the previously defined function make message and the fetch response function. So these are the helper functions that I defined at the end of section 1. Okay, so I'm reusing these helper functions to like pass the message to the pipeline and also extract the response. Okay, so yeah, for this sentence, where is the nearest hospital? The model translated it into French. Okay, so these were some examples of few shot prompting. So are you able to follow till now? If not, you can post your questions to the Q&A section. Okay, I can see a few thumbs up. Okay, so let's continue. So now section 4, we have chain of thought prompting. So in chain of thought, we can mix it with zero shot or few shot. So there are 2 variants. In zero shot chain of thoughts, we just say, let's think step by step. We add this to the prompt, and the model will give the answer in step by step manner. And we also have few shot chain of thought, where we give some example of chain of thought reasoning, and we ask the model to follow similar chain of thought reasoning. So here's an example of a zero-shot chain of thought. So the system prompt is, you are a helpful math tutor, and the user prompt is, a store sells apple for ₹15 each and oranges for ₹20 each. If Maya buys 4 apples and 3 oranges, how much does she spend in total? So we add this sentence. Let's think step by step. We add this to the prompt so that the model will give the output in step by step. Yeah. So this is the output that we get. So as you can see in the prompt, we have the step-by-step explanation. So the model is giving step 1, step 2. Step 1 is calculate the cost of the apples. Step 2 is calculate the cost of the oranges. Step 3 is calculate the total amount Maya spends. So like that, we have the step-by-step reasoning output. And then the total amount that was calculated is ₹120. Okay, so that was a zero-shot chain of thought example. Now we have a few short chain of thought example. So here the system prompt is, you are a logical reasoning assistant. Always show your reasoning before the final answer. And in the user prompt, we are providing some examples. So the first example is, a train travels at 60 kilometers per hour. How far does it go in 2.5 hours? So in the reasoning steps, we provide the steps. Like step 1 is the formula of distance, that is speed into time. And step 2 is to put the values and compute the distance. So that is one example in the prompt. Another example, this one is about, a shop has 200 items, so 40% are sold, how many remain? So for this, we show the step-by-step reasoning, step 1, step 2. And then we ask the model, a recipe needs 3 cups of flour for 12 cookies. How many cups are needed for 40 cookies? So now if I run this cell, yeah, so the model followed that structure. So it gave the reasoning as step 1, step 2, step 3, step 4. So in 4 steps, it reasoned and it gave the answer as 10 cups. Okay, so we can also use chain of thought for logical common sense reasoning. So here for example, the system prompt is, you are a logical reasoning assistant. Think step by step before answering. And the prompt is, all mammals are warm-blooded. Whales are mammals. Dolphins are mammals. Sharks are fish, not mammals. And the question is, are whales and dolphins warm-blooded? Is a shark warm-blooded? Let's think step by step. So let's see what the model says. Okay, so the model gave the answer. To analyze this question, let's analyze the information. So to answer this question, let's analyze this information step by step. All mammals are warm-blooded. This is a general statement that applies to all mammals. Whales are mammals. Since all mammals are warm-blooded, whales must also be warm-blooded. Dolphins are mammals. Again, since all mammals are warm-blooded, dolphins must also be warm-blooded. And sharks are fish, not mammals. This statement tells us that sharks do not belong to the mammalian category, but it does not provide information about the temperature regulation. Okay, so from the information provided, we can conclude that whales and dolphins are warm-blooded as they are mammals. However, we cannot determine the temperature regulation of sharks based on the given information. We only know that they are fish, not mammals. So the answer to the question is, whales and dolphins are warm-blooded. We cannot determine if a shark is warm-blooded based on the given information. So this chain of thought, these steps, 1, 2, 3, 4, these steps, this help the model to come up with this answer. Yeah, so that was chain of thought prompting. Now coming to meta prompting. So in meta prompting, we ask the model to generate the prompt itself, or we give some prompt and ask it to improve the prompt rather than giving the right answer. Okay, so let's see some examples of meta prompting. Yeah, so the system prompt is, you are an expert prompt engineer. When given a task description, write a clear, detailed prompt that another AI model could use to complete the task accurately. And the user prompt is, I want an AI to help students understand a complex scientific concept by using simple analogies and everyday examples. Write a prompt for this task. Okay, so if I now run this block, yeah, this is what the model returned. Here's a detailed prompt for an AI model to help students understand a complex scientific concept using simple analogies and everyday examples. So task description. So like this, the whole prompt, this was generated by the model itself. Okay, so task description, specific requirements, input parameters, output requirements, all these are specified in the prompt. Yeah, so this was an example of meta prompting. So here is another example of self-refinement. So the model will critique itself and improve the prompt. So the system prompt is, you are a writing assistant who helps improve text quality. And the initial user prompt is, write a short product description for a smartwatch. Okay, so we get an initial output and we create another prompt where we say that here is a product description with the prompt that the model gave. Then we say, critique this description, what is weak or missing. Then rewrite it to be more engaging and persuasive. Then we again pass this prompt to the model and see how it refines itself. Okay. Yeah, so this one is the initial output that the model gave from the first prompt. That was just write a short product description for a smartwatch. So this prompt gave this output. Here's the short product description for a smartwatch, and then this the features and all this. After that, we took that prompt and added these lines, critique this description, what is weak or missing, and then rewrite it to be more engaging and persuasive. So for that, the model gave this response. So it gave 5 points. It critiqued itself. The prompt, the description that the model generated, it then critiqued its own generation, and then also gave a new description. So here's the rewritten description based on the critique. So the first point was, the description is a bit generic and doesn't provide a clear unique selling point for the Pulse Pro smartwatch. The list of features is straightforward and lacks a compelling narrative to tie them together. The language is somewhat cliched, with phrases like ultimate wearable companion and always on top of your game. So like this, it gave 5 points of critique, and then rewrote the prompt with those critique points. Okay. So now coming to the next example, task planning. So the system prompt is, you are a project planning assistant. First, create a numbered step-by-step plan, then execute each step. And the prompt is, write a beginner's guide to starting a vegetable garden at home. First, list the steps that you will cover, then write the guide. Okay, so here is what the model returned. Step-by-step plan, planning and preparation, choosing the right location, preparing the soil, selecting the right vegetables, preparing the garden bed, preparing the vegetables, watering and maintaining, pest and disease management, harvesting and enjoying. And then it expanded the plan. So step 1, all these points, then step 2, all these points, step 3, all these points, like this. It generated the plan, and you can see that the prompt ended abruptly. So this is because of the limit of max new tokens equal to 500. So after this token, that limit was crossed. So this is where 500 tokens is finished. So it will not generate any more tokens. So you can experiment with this by increasing the max new token parameter and to let it generate even more tokens and see the output. Okay, so in the final section, this is a try it yourself section. So in this section, there are 3 examples of tree of thoughts prompts. So first example was a business strategy problem. Second example is a logical puzzle. And the third example is a creative writing with tree of thoughts. So this section you can execute on your own and see the results. And so that brings us to the end of this demo. Here is a summary of the techniques that were shown, the core ideas and what it is best for. Okay, so now we can move on to the Q&A section. Oh, sure. Okay, so you can scan this QR code and answer this question. Are you able to grasp the hands-on session? Yeah.
Sir, I'm unmuting some learners. Suresh, you are unmuted. Suresh Nagaranjana.
Thank you. Thank you so much. Am I audible?
Yes, yes. Yeah, you are
Just-
audible.
Professor, in a practical applications, how do we determine the optimal number of reasoning paths to sample for self-consistency? Is there a trade-off between improved accuracy and computational cost that we should consider?
Obviously, first of all, depending on the problem, your problem is simple enough, definitely you don't have to go for this complex reasoning task, okay? Reasoning complex kind of prompting, because it will incur more overhead. Now, in the self-consistency, obviously, you can think that you have more branches, you will have this majority voting. Now, if you include more branches, obviously, it will incur more token cost and everything. Now, there is a decent number of branches which usually keep in odd numbers in the standard assembling or the majority voting kind of task. So 5 to 7 is basically fine. Now, based on your problem, it may vary, but in the self-consistency part, or basically in tree of thought, if you create a balance between the performance and the branching factor, okay? If you increase the branching factor, obviously your cost will increase. Accordingly, you can get better accuracy. On the other hand, you have to optimize between them to find a sweet spot, and it depends on the problem. So if your problem is not that complex one, first idea is not to go for this kind of complex prompting. If it is basically analytical, you can divide it into sub problems, you can have reasoning problems, you can have planning kind of things, then you can go for this self-consistency of tree of thought kind of thing. But the branching factors on a thumb rule 5 to 6, 7, it generally works well. Yeah. 3 to 7 it does.
So how many reasoning paths are typically needed for self-consistency to be effective?
That's what I'm telling. If you are creating this branching factor of 3 to 7, that means it will create 3 different, or basically 3 to 7 different kind of solutions. And ultimately, it's taking the majority voting out of this. In self-consistency, there is nothing called independent branching factor. These are the 3 to 7 ways, independent ways it solves the problem, and ultimately, you're taking the majority voting out of it. That is the result of the self-consistency. And the tree of thought, you have this branching. So you can control the branching factor in different levels. And out of that, it basically selects the best possible path that basically leads you to the solution from input to output. So that is the
Thank you so
difference.
much.
Yeah.
Thank you so much, Professor and Manish. Thank you so much.
Arav Santosh Kumar, you are unmuted. Please go ahead and ask your query. Arav. Anand Sri. Anand Sri, you are unmuted.
Sir, hi, this is Anant. Sir, my question was initially on that chain of thought and with zero shot. So can we combine them to maximize the output, or do we only have to go like with one of them at a time?
So first of all, maximize the output means what? You are talking about the performance or accuracy. Now,
Accuracy, sorry.
Yeah, so zero shot is basically you can directly ask. So the first question is basically chain of thought, you need more tokens, more overhead. Now, given the problem, first you have to decide, do I need that kind of complex prompting or complex reasoning process? Is this task is that complex? If it is simple task, then we can directly go with the zero shot. If we are not satisfied with the response, then we have to go for the chain of thought kind of reasoning setup. Now, if you use the chain of thought, you do not need any zero shot mode anymore. And if you have to generate the reasoning, then you can go with the zero shot chain of thought. There is a difference between the zero shot and zero shot chain of thought. Zero shot means directly asking the question. Zero shot chain of thought means you have to add this kind of prompts like let's think step by step to generate the reasoning processes. And that mostly works if you have these complex reasoning problems. And one thing, it is not only mathematical problems, any kind of reasoning problem. It could be a planning problem, it could be a scheduling problem. Many times we work on the logistics, so we have to plan that what are the possible routes that we have to optimize this path. All these problems that comes under this category.
Anand Shri, hope that's clear. Milan Sheth, you are unmuted. Milan.
Yeah, I had a question regarding basically sarcasm and how it's handled in the assignment, right? Why did it perform better while using these models compared to the assignment question that we had where we used cross attention? I think it was single layer cross attention and by LSTM and fast text. So it couldn't handle sarcasm there. But over here, I could see the sentiment analysis cell number 17 could handle it. Can you explain why that happened?
No. So are you asking from the previous assignment?
Yeah, I compared the previous assignment versus today's Python
Okay,
notebook
so
cell
could you repeat the
17.
question once?
Yeah, so the previous assignment, we used cross attention, BiLSTM, etc. to do the sentiment analysis. Okay, it
Okay.
couldn't handle sarcasm well. But
Okay.
today's the course, the hands-on, I could see cell number 17, sentiment analysis handled it pretty well.
Okay.
Can you
Now,
explain the differences? Yeah, sorry.
yeah, in the previous course, it is basically you have trained the biastism with the cross attention mechanism, right? And what is
Yes,
your training data? Your training data is the sentiment.
yes, it was movie reviews.
Yeah, so basically, then you are expecting to solve the problem of the sentiment.
Yes, but how did this perform better? Like what was the difference? Like why did this model which we use today perform better?
Means perform better in the performance.
It could
Sentiment.
handle sarcasm.
Okay.
Sarcasm.
Okay. Previous day, did you use any LLM?
Yeah.
So previous day when you use the
Oh, it
BiLSTM
was just
and
BERT. Yeah,
yeah,
it
it
was
is a
just
BART,
BERT.
right?
Yeah,
Yeah.
yeah.
So it is not an LLM. It's basically an
Okay.
auto-regressive language model, okay? And you have
Yes,
fine-tuned it for this particular sentiment detection task.
correct.
Today, probably he used this LLM to basically predict this sentiment part. Now, in LLM, we have this pre-trained memory, and it is basically a generative model. Okay, so it is customized for this particular sentiment part, but along with that, it might perform some for the sarcasm detection task. But if it is basically customized for the sentiment detection, you cannot expect that it will work equally well for the sarcasm, because sentiment and sarcasm, these are two different tasks. So when you are fine tuning for the sentiment detection task, for certain sarcasm part, it may work because they are related in some way, but they are not the same task. So if you just use any kind of previous customized model like BiLSTM or basically fine tuned BART, it is going to work only for the specific task for which you are fine tuning. You cannot expect it to go for others. It can work if the task is related. For example, sentiment and sarcasm, it is related, but they are not the same task. Sarcasm is much harder than the sentiment detection. Today's model, it also works for the some use cases, but if you go for other complex sarcasm part, it will check that you can check that it is not going to work for those complex sarcasm part, because if it is trained on, even if you trained on the sarcasm data itself, you still find that you may not get that much accuracy beyond 70 or something. So those use cases will always come.
Yeah, I'm trying to understand the science behind why this happened. I got the gist of it. But
So
why
whenever
it
you are
happened?
using this LLM, you are using a pre-trained memory, which is basically GNI model. So it is,
Yeah,
you do not know the pre-trained data. It might already see some kind of data that you are trying with. Okay. So in that case, it basically just gives the response from the pre-trained memory that it is there. So
okay.
you may get some responses out of it, but if you really form some complex ones, and if you do not give that response or basically that kind of input to the LLMs, you can see that the desired result is not coming. So
Okay.
sarcasm is not an easy task. So you may not get that response for all kinds of inputs. You can try this. So you have this notebook, you can try.
Yeah, yeah. Thanks, Professor.
Devanjali Ghosh, you are unmuted. Please go ahead and ask your query. Devanjali. Ramya Roy, you are unmuted. Ramya, you are unmuted. Please go ahead. Ramya.
Hello, sir. Good afternoon, sir. Can you hear me?
Yeah.
Sir, actually, the same question what Shet Madam has asked, I asked the same thing. Thing is that, say, suppose the model I'm providing a sentence like, say, a spy, an agent chases a spy with binoculars. So then I ask the model, who is carrying the binocular? Okay, so that in that sarcasm, how the model actually react to that sarcasm? So my sentence is that an agent trails a spy with binoculars, and I ask the model who is carrying the binoculars. So in that way, how the model actually helps here.
Okay, so
I think the same question like Shet Madam has asked. I have the same thing like.
Okay, sarcasm detection task means given an input, you have to detect that whether it's a sarcastic sentence or not. Is this your task, or basically given a particular sentence?
Yes, sir.
Yeah. So basically, if your task is given a sentence, whether it's a sarcastic sentence or not, you can give that input and model can predict it is basically sarcastic or not. But if you want to get any specific answer from that particular question, like you are asking that who is wearing the binocular or something, like you want to get that answer, means from the question.
Yes, sir.
No, these are the two things. One, given the input, you just want to get the class, that whether it's a sarcastic or not sarcastic. And another task, given the input, you want to ask some question like who is wearing the binocular, and you want to get that answer. Which one is the task?
So both.
Huh?
Both the queries. So
Okay.
model asks both the queries. So,
okay, so these are the two tasks. One part, if you want to detect sarcasm or not, it's a classification problem. If you want to get the answer, it's a QA problem. So first of all, given the model, you can ask that whether the sentence is sarcastic or not. That is one part, model can tell. And if you want to get a specific answer, given the particular text, who is wearing the binocular or something, it is basically simple answer extraction. From the given text, model will try to find out the answer for that. So if you basically jointly ask these two tasks, you are supposed to get answer for both the part. Now, this sarcasm detection task, as I have said, it is not an easy task for the sarcasm detection. It depends on the model ability, that whether it will give you the desired response or not. In many cases, it might be wrong if you do not properly give examples to the model to make it familiar with the context.
okay, sir. Thank you, sir. Sir, one more thing. So suppose in the GPT model, okay, I ask a model to take a role. Okay, like say suppose I ask a model to take role as a say graphics designer or Python developer or React developer, whatever. And in the second prompt, say suppose I have taken the input, say suppose I've given a system prompt and I have given a user prompt. So how these two prompts are different?
Okay, so first, when you are telling that, okay, you want to ask some question from the graphic designer, how would you like to set the context for the LLM? Okay, so this system prompt, you can specify that, okay, now you can assume that you are a basically graphic designer expert or something, and you are supposed to answer certain questions from this particular domain. This is basically a very generic comment for all the users that are going to ask graphic related question. That basically you can set as your system prompt. Now, when it comes to the user prompt, different users may have different kind of queries from this graphics domain. Now they will start asking those questions and LLM is supposed to answer. Now, while you giving this first system prompt, you are setting the context for the LLM. That means you are telling that, okay, now you are supposed to give answers for the graphics related questions. And in that particular session, other users, they will consequently start asking any graphics related questions, and it will, if it has the answer, LLM is supposed to give the answer for those questions. Now, what is the benefit of that setting system prompt? In between, if someone comes and asks some other question, might be law related question or medical related questions, then ideally LLM would basically simply tell sometimes that, okay, I'm not supposed to give the answer for those questions in this round. That is the utility of the system.
Yes. Thank you, sir.
Parul, you are unmuted. Parul Khatri.
Hello.
Hello.
Hey, good afternoon, Professor. So, my question is that I understood that self-consistency is using sampling to generate the different path and then give the output. So, are we using the same approach in TOT, or is it using something else like greedy decoding at each level?
No, they do not use the greedy decoding. If you look into the self-consistency, this is basically the multiple ways of solving the problem. And ultimately, it is taking the majority voting. That is basically ensemble kind of approach to select the result that is basically supported by most of the solution techniques. Okay.
So
Now,
at
when
each path, basically, we are like giving the value of like temperature, top K and top P, and then identifying that the correct result, basically.
you do not know the correct result. So you are just asking a question to the LLM, and you are basically giving or basically telling that we have to follow the self-consistency prompting strategy. Okay. Now, what basically based on the prompt, LLM decides that, okay, if I have to follow the self-consistency technique, it will basically tries to solve the problem in different ways. So it is basically one hop path. Given the question and the prompt, it basically generates multiple solutions for the same problems in a different reasoning ways.
So
Now,
on what basis it is generating the multiple solution,
yeah, that the
multiple paths?
parameters that you are telling, the paths basically. So some reasoning steps might be it solves the problem at once. Some reasoning steps might be the simple steps, like it follows, suppose example, you have to do 2 plus 3 into 5. So one reasoning step might do it at once. That in the bracket it can put 2 plus 3 multiplied by 5, or otherwise if you can first do that, okay, I have to first do the the addition, if you put in the bracket, and then do the multiplication. Now if you do step by step, or you can basically do it at once in a single step. Now these things basically depends on the parameters that basically LLM is solving. Now once it solves across this multiple branch, each of this branch it returns some result. Now all these results, it's checked that which result is supported by different paths or different solution, and that result is basically taken out.
Okay, okay.
This is
So is
basically
there any way to find out the best fit value for temperature, top K and top P?
there is no best fit value. It's, you can set it empirically. Generally, the thumb rule is low temperature you should use for the deterministic tasks. For example, when you are basically solving classbook questions, or basically you are trying to check that whether this information is factual or not, where you know basically I do not want to speculate, or I do not want to generate some kind of creative thing, then basically we set the temperature in the low range, 0, 0.1, 0.2, something like this. If you are basically writing blogs, or you are doing some creative activity, or basically you want to generate some ideas, doing brainstorming, in those cases generally we set the temperature high, because we want to get some kind of diverse output, new things that we expect from the LLM. So it depends on the application that you are using. You have to set the temperature accordingly.
Okay. And for low temperature as well, there would be some range. So how I will like get to know that which exact value is the optimal for this for keeping this temperature as low? So
There is
is there any
nothing.
human expert required to validate that, and
No.
how it will be basically?
There is no human expert as such. So it depends on the task. If you suppose you are solving a particular kind of task for a long time, automatically you have some knowledge that is called the domain knowledge, that you can easily know that this temperature is going to work for this kind of problem. For other kind of problem, the standard validation set is there. If you vary the temperature on the validation set, you can check the performance and say, okay, this temperature is probably working best for this kind of problem. And then accordingly you can set that temperature for that particular category of problem. For example, the temperature that works well for the sentiment detection, you cannot expect that it will also going to work for the sarcasm or for the question answering. So it will vary accordingly. Okay. But if you are only solving this sentiment detection for a long time for this domain, suppose this movie review, something, you have that human knowledge or basically domain knowledge that this temperature is going to work for me. In that case, from human expertise, you can directly set that value. Otherwise, the validation set will help you to decide the temperature, the sweet point basically in the temperature.
Okay. Thank you so much.
Sir, keeping the interest of time in view, we can close this session.
Okay.
Thank you, everyone.